Have you ever opened a YouTube video to learn real-time applications, only to watch someone import a paid third-party service, call it a day, and leave you with zero understanding of how WebSockets actually work? You know, the exact thing that interviewers will grill you on. You know the vibe. They drag and drop a library, use a black box API, and tell you it's magic. But then you walk into an interview, and they ask you to explain the 101 handshake, ghost connections, real-time message patterns, or head-of-line blocking, aka why streams freeze. And suddenly, that magic disappears. In 2026, anyone can pay for a service or generate code with AI. But engineers build the service. Hi there, and welcome to the course that skips the as a service shortcut and teaches you how to engineer real-time apps from the ground up. And here's my promise. By the end of this video, WebSockets won't feel like magic anymore. First, you'll understand the core mechanics of WebSockets, how a WebSocket starts life as HTTP, what the 101 switching protocols response actually does, and how full duplex communication lets the server push data instantly. Then, we go from theory to production. You'll learn how to keep thousands of connections stable, how ghost connections silently kill servers, how ping-pong heartbeats keep everything alive, and how to structure messages so your server always knows the intent. And once that's locked in, we'll cover the patterns that power every serious real-time product. Broadcast versus unicast versus rooms, pub and sub architecture for live sports and large-scale event streams, acknowledgements for reliability, how back pressure forms, how real systems avoid memory blowups, and when WebSockets are not even the right tool. That's a lot to learn, right? And the best part is, that's just the foundation. Because once the fundamentals are locked in, you'll take everything you've learned and build Sports, a high-fidelity live sports match engine that broadcasts scores and play-by-play commentary in under 10 milliseconds. And you'll build it by using a real production stack, Node.js for the fast event-driven core, Express for the handshake and REST APIs, native WebSockets using the WS library, so we implement the protocol from scratch for maximum control, Postgres for storing sport matches and commentaries, and the Drizzle ORM for type-safe database interactions. Then, we ship it like an actual production app. We'll use Arcjet to secure the real-time system, blocking bots, rate-limiting abuse, and stopping DDoS attempts before they even hit your logic. We'll use React to build a high-performance UI that updates like a stadium scoreboard in real time. We'll use Site 24/7 to monitor server health, user experience, and network latency so that 10 millisecond broadcast target stays consistent even under load. And while we build this, we're not sacrificing code quality. You'll implement clean, industry standard practices with the help of CodeRabbit, your AI code reviewer that catches architectural flaws before they reach production. Finally, we'll deploy it using Hostinger. So here's my promise. This course is enough to lock in your real-time fundamentals and let your confidence speak in any interview. You won't just say, yeah, I can build a chat app. You'll explain exactly how the data moves through the wire. Look, if you're serious about leveling up from watching tutorials to actually becoming hire ready, you'll love JS Mastery Pro. It's where I go beyond the build this app stuff and teach the engineering mindset behind the code. Inside Pro, you get full premium courses like the Ultimate Next.js, testing, animations, JavaScript, SQL, 3JS, and more. Quizzes after every lesson, so you actually lock in what you learn. Interview practice with our AI interviewer, so you can train for real technical interviews the same way you train for a sport. And we're also launching the Ultimate Backend course and our AI engineering courses next, and our Pro members get early access. You also get access to our private Discord where you can ask questions to real human beings and get help fast. If you want to check it out, I might give you a special discount just because you're coming from this video. Give it a shot. The link is in the description. Imagine you're at a restaurant. You're starving and you're waiting for your pizza. In the world of HTTP, the only way to know if it's ready is to keep asking. Is it done? No. What about now? Still no. That's polling. It's how early real time apps worked. Your browser would constantly check the server every few seconds just in case something changed. And it's super wasteful because every time you ask, you're sending a full HTTP request with a bunch of headers just to get a tiny response back. So if HTTP is so inefficient for real time, how do apps like Discord or live chats feel instant? Because they don't keep asking. They keep an open connection. And they do it by using a protocol. A protocol is basically the rules for how two computers communicate. HTTP is a request response protocol. It's amazing for websites, APIs, and loading pages. But it's terrible for fast back and forth conversations. For real time apps, we need a protocol that supports a permanent two-way connection. That's WebSockets. A WebSocket connection stays open so both the client and the server can send messages anytime. This is called a full duplex. Fancy term, simple meaning. Both sides can talk at the same time. So the server can push updates the instant they happen, typing indicators, live comments, multiplayer movement, notifications, all of it. Okay, but isn't that expensive? It sounds expensive, but it's actually cheaper than polling. It's less expensive because with polling, every check sends large HTTP headers. But with WebSockets, once the connection is open, messages are tiny. It's also more efficient for servers because it's harder to handle thousands of HTTP requests opening and closing than to keep thousands of WebSocket connections just sitting there idle. It's also better for mobile because polling wakes up the phone over and over again, but a single open connection is usually easier on the battery. Now, let's talk about the WebSocket handshake. This part is key. It's the coolest thing because a WebSocket starts as a normal HTTP request, but then the browser adds a special header basically saying, hey, server, can we upgrade this connection to WebSocket? If the server supports it, it replies with HTTP 101, switching protocols. And the moment that happens, HTTP is done. And now you have something called a WebSocket tunnel. Open, persistent, and real time. Just like HTTP and HTTPS, WebSockets have two modes. WS is unencrypted, and then there's WSS, which is encrypted. In production, you always use WSS. And now that you know what WebSockets are, very soon I'll show you how to build one. You just learned that the WebSocket handshake upgrades HTTP into a persistent open connection. But once that phone line is open, how do we actually manage the conversation? Let's break WebSockets down into the real production architecture. And I'll do that by telling you a bit more about the life cycle of a WebSocket connection. Because a WebSocket connection isn't just on or off. It has stages. Think of it like a high-speed train system. You connect, you ride, you make sure nobody vanished mid-trip, and you clean up properly. Let me explain what I meant. First is the connect, or the knock. It starts with one line. You set up the socket by creating a new WebSocket on a specific port. And the moment this runs, the browser sends an HTTP GET request, but with a special header that says, I want to upgrade this connection to use WebSockets. That's the upgrade request, or the switch. If the server accepts it, it replies with 101 switching protocols, and that's the moment the relationship changes. HTTP ends, the tunnel stays open, and now both sides can send messages instantly whenever they want. And now we get to the biggest architecture shift. The state, or the memory. HTTP by default is stateless, which means that the server forgets you after every request. WebSockets, on the other hand, are stateful. The server now holds a reference to your socket in memory, and that's how it can push data to you instantly. But this also creates a new problem: ghost connections. What if someone loses Wi Fi? What if their phone dies, or if they close the laptop without properly disconnecting? Now the server thinks the connection is still alive. It keeps holding the socket in memory. These are called ghost connections. And if you don't clean them up, your server eventually dies, slowly, just from holding onto ghosts. So, what's the fix? Well, in production, WebSocket servers use something called a heartbeat, or oftentimes called ping pong, because the server sends a tiny ping and the client responds with a pong. If the server stops hearing pongs, it assumes the client is dead and terminates the socket. That's how you prevent ghost connections. Now, you might think, wait, if we ping every 30 seconds, isn't that basically polling? Well, not even close, because polling is an entire HTTP request. A WebSocket ping is basically a tiny impulse on an already open tunnel. It's massively lighter, massively cheaper, and far easier on the battery. But now that you understand the connection, let's talk about the data transfer. Like, what actually gets sent through that tunnel? With WebSockets, you don't send web pages. Obviously, right? You send messages. And there are two main types: text, or JSON, and binary, raw. Most real-time apps send JSON. Things like user is typing, new message, score updated, notification received. That's usually socket.send, you stringify it, and you send over some data, like user with an ID of 42 is typing. Human readable, easy to debug, and perfect for 99% of the apps. But then we also have binary. Binary is what you use when things get serious. Audio streaming, video frames, multiplayer game states, large payloads. Instead of sending text, you send raw bytes using array buffer or blob. It's faster, smaller, and more efficient. But how does the server know of what type of message it is? Well, at the lowest level, WebSockets use something called an opcode. It's basically a label that says, this frame is text, this frame is binary, this frame is closing, and this frame is ping pong. You won't have to deal with opcodes directly most of the time, but it's what makes the whole protocol work cleanly. And then there's back pressure. Advanced but important. And last major concept I want to teach you, I promise. Think about what happens if your server is sending updates like crazy, but your user is on a slow internet connection. New messages start piling up in memory. That's called back pressure. Production apps monitor how much data is buffered, and if it gets too high, they slow down the sending rate so the server doesn't explode. Literally. This is an advanced concept, and you won't need it for every project. But once you build real systems, this becomes a big deal. And those types of big deals are the exact reason why I'm working on the ultimate backend course. We're going to dive super deep into advanced concepts just like this one. So if you're interested, you can join the waitlist through the link in the description to get the initial lessons as soon as they're ready, and then the full course in about 2 months. I'll keep you updated. But now that you understand the architecture, like you connect, you upgrade, you keep state, you detect ghost connections, you send messages, and protect your server under load, now let's actually build it. Okay, enough theory. You've learned a ton about WebSockets. But now let's do one real thing. Actually create one. But before you write a single line of code, you need to choose your weapon, because there are 3 different options for creating WebSockets. There's the Socket.io library, Pusher or Ably, which are WebSocket services, and then the WS library. Let's go over all 3. Socket.io is the most popular real-time library in Node.js. It gives you a full management suite on top of WebSockets, reconnects, rooms, fallbacks, the whole package. But it's heavier. You ship extra client code, and every message comes with extra overhead. It's great for speed of development, but not for the purest WebSocket experience. Then there are WebSockets as service tools, such as Pusher or Ably. You don't host the server, you just pay them and it just scales. It's the easiest path to production, but the trade-off is cost and control. It's amazing for teams that want done-for-you solutions, but not great if you want full ownership of the system. And then there's the WS library. This is the low-level but high-performance route. It's fast with minimal overhead, and it matches the browser WebSocket API closely. The catch? You build features yourself. Rooms, reconnections, heartbeats, auth logic, all you. But if performance and low latency matter, this is the real deal. So I'm happy to say that you requested it and you got it. In this course, we're using the original WebSocket library. Because if you start with Socket.io, you'll learn magic. But if you start with WS, you'll learn the actual protocol. And once you understand native WebSockets deeply, switching to Socket.io later is super easy. That's my promise for this course. So just before we build it, let me just talk for a second about the WebSocket lifecycle. And please don't skip this as it matters a lot. A WebSocket is basically a state machine. If you try to send data in the wrong state, you'll get bugs, broken messages, or crashes. So we need to understand 4 different states. The first one is connecting. Handshake is still happening. Don't send yet. Then there is open. This is the safe zone. The tunnel is live. You can send. There's closing. Connection is shutting down. Stop pushing data. And then there's closed. It's dead. Time to reconnect. And yeah, you can check that anytime using socket.readystate. Now, we'll be managing this WebSocket from both the client and the server side. So let's talk about the server-side events with WebSockets. Because on the server, you're the host. You're listening for clients joining, sending data, disconnecting, crashing, all of it. So your starting point is the connection. This is your entry point. You declare a new WSS.onConnection function, and within it, you can have all the information about what's happening with the socket and the requests coming in, such as learning when new clients are joining in. Then there's the message. This is incoming data. In WS, it usually arrives as a buffer, so you have to convert it. You do that by saying socket.onMessage, you get the raw data, and then you console log it and do whatever you want with it. Then there's the error, and this is critical. This is the event that people ignore and then regret. If you don't handle it, one bad connection can crash your entire node process. Socket.onError, and then you handle it gracefully. Now, there's also the other side, how you're handling the client-side events in the browser. Because on the front end, you're just a participant. There's an open event, which means that the handshake worked, and now it's safe to send. You can listen for an open request, and then do a console log or send a message, because now you're connected. Then there's the message where you receive server updates. You can parse the data coming in and display it. And finally, there's a close, which simply means disconnected. Keep in mind, your server is the boss and is sending all the data, but on the front end, you're just a participant. If you want to pause your screen for a second, I can give you a final quick cheat sheet with most important methods and listeners on both the server side and the client. But once we go through it throughout this course a couple of times together, you'll be able to remember it easily. On the server, we have the connection, message, error, and close. And on the client, we have the new WebSocket to create it, and then on open, message, error, and close. So now that you understand the lifecycle and the events, let's get our hands dirty and actually build. something real. And let's dive right into the demo. You can create a new empty folder on your desktop and call it something like WebSockets, and then open it up within your editor or IDE. Once you're in, you can also open up the built-in terminal. I'm using WebStorm in this case. And then, if you make sure that you're in the right folder, go ahead and run npm init-y. This will initialize a new Node.js application with the default settings. And a Node.js application is nothing more than a package JSON that contains a name, a version, description, the main starting point of the application, and some scripts needed to run it. And most importantly, it'll contain a list of dependencies or libraries that we add to it. And one of the main libraries that we want to install, maybe the only one for this project, is going to be the WS library, a Node.js WebSocket library. It's simple to use, blazing fast, and thoroughly tested WebSocket client and server implementation. Most importantly for us, not only the fact that it is popular with 130 million weekly downloads, but the fact that it is tested and that we know it works properly and is well documented. So let's go ahead and install it very quickly by opening up our terminal one more time and running npm install WS. You'll be able to see that it is super lightweight, so it'll get added to our dependencies array in a matter of seconds. Then we want to use ES6 within our application, so we have to manually modify the type of our app from common.js to module. And then we'll create a starting point of our application right here by creating a new file called server.js. And this is where we're going to implement our WebSocket. So first things first, we have to import it by running import WebSocket Server coming from WS. Then we can initialize a new standalone server by saying const WSS is equal to new WebSocket Server, and we can do it on port 8080. This creates its own internal HTTP server just for the handshake. Then we have to deal with the first event when it comes to WebSockets, and that is the connection event. You can do that by saying WSS.on, specifically on connection. We want to get access to the socket and the request. Once we have it, we can set it up. This connection event will fire after the 101 handshake is verified. Socket will contain the individual connection to one client, and the request will contain the headers, such as cookies, IP address, and more from the upgrade request. Now, if you hover over the socket or the request, you'll see that it just says unused, with no additional information about it. That's because right now, even this on function on the WebSocket server is not recognized. So how can we actually get more information about what we're actually doing here? Well, if you open up your terminal and run npm install --save-dev @types node and @types/ws, you'll get all the typings for the libraries that we're using, which means that immediately you'll no longer have squiggly lines right here over the on, and instead it'll recognize that this is the on connection event, which now allows you to try to get access to the IP address by saying request.socket, and you can see that now it knows that it is there, .remote address, so it autofills it for you and also tells you what it is that you're retrieving, such as the string representation of the remote IP address. Perfect. This is exactly what we wanted to get. So even though we've switched protocols, we can still see the original HTTP request data. That includes the full request headers if you want to grab the cookies, or the request URL if you want to grab params, and it also includes the remote address, which is the physical IP address of the client. Finally, we are ready to turn on the socket.on event, and specifically we'll be waiting for the message. From the message, we are retrieving the raw data, and we might as well go ahead and console log the data so we can see how it looks like. So I'll just put it within an object. Both the key and the value say raw data, so we know where this console log is coming from. Let's also properly close this one right here. And once we do, we can get access to a list of all currently active socket objects by saying wss.clients dot for each. And for each one of these clients, you can define what you want to happen. Specifically, we want to iterate through them and then push the data to everyone. So I'll say if client dot ready state, remember when we were talking about it in the crash course, if that is equal to 1, in that case, we can run client dot send, and we can say something like server broadcast and define the message that is coming in. But of course, this message will be the raw data converted into a string, because as we learned about, the raw data is actually a buffer or binary. So we need to use the toString to convert it to text. So I'll say const message is equal to raw data dot toString. Now, why did I specifically use a ready state of 1? Well, remember when we were talking about different states before, they looked something like this. There we go. We have 0 for connecting, 1 is open, the only state where you can safely use the .send command that we used right here, 2 is closing, and 3 is closed. So always remember this when you're referring to client-ready states. In most cases, you'll be checking whether it's open. If you try to send a message to a client in a state 2 or 3, your server might throw an error or leak memory. So always make sure that you're talking to open clients. Now, here's a pro tip that is unrelated to WebSockets specifically, but it's a good programming habit in general. You never want to have something called magic numbers, like this 1 right here. Like, what does it mean? So instead, you can either declare constants yourself, or in this case, WebSocket provides them for us. So instead of checking for the equality with the number 1, which doesn't mean anything, you can check for the WebSocket that open state. So if client ready state is equal to WebSocket open, we can go ahead and send a message. Now let's exit this on message listener, and right below it, we'll create a socket.on error listener, because sockets are fragile. And if a client's internet flickers, the socket might actually throw an error, and if you don't catch it, the whole server will crash. So let's simply say console.error, and here we can do some kind of a console log where we say error. You can even declare for which IP address the error is happening, and that's exactly why I got access to it right here before. So we'll say error for this, and then we can also display the error message. Perfect. Finally, you also want to do some socket cleanup. Right at the end, I'll say socket.onClose. For now, we can simply console.log and say something like client disconnected. And this right here is your first very own WebSocket server. So let's go ahead and run it by heading over to our package.json and changing the main part of our application to server.js, which is the name of our file. And I'll also add a script, which is going to be a dev script, where you can say node -- watch to keep track of the changes, server.js. Once you add that script, you're able to open up your terminal, run npm run dev, which will spin up your WebSocket server. If you just spin it up like this, you won't see anything in your terminal. But if you head back over to your server.js, and at the bottom, you add some kind of a message like console log WebSocket server is live on ws:// localhost 8080, you'll be able to see this message appear right here. But how exactly is this working? You didn't use Express, right? You didn't even use the HTTP module to start. You just ran a new WebSocket server on port 8080. You've been told for years that to run a web app in Node, you need Express. So how did our code just work? Well, the WS WebSocket library is doing the heavy lifting under the hood. When you pass a port to a WebSocket server, it realizes that there is no HTTP server to hijack, so it spins up its own internal Node.js HTTP server automatically. It creates something known as a zombie HTTP server that only exists to listen for that upgrade handshake. And once it sees a valid WebSocket connection, it handles the logic and holds the TCP connection open. In a small project, letting WS manage the port is totally fine. But in production enterprise app, you usually attach WS to an existing Express or Fastify server so they can share the same port. One port, two protocols. I hope that's clear, But the next question is, how can you test if this is even working real time or not? Well, there are different ways. One is through the browser, and the other is through the terminal, and using some professional tools. So let's try each of them one by one. In this case, you don't need an index HTML to be able to see it in the browser. You can hijack any website on the internet to test your local server. Make sure that it is actually running. Then open up your browser, go to any website. I'll naturally head over to jsmastery.com to check out some courses while I'm here. But jokes aside, the only thing you have to do is right-click any page within your browser, go to Inspect, and then to the console. Once you're in there, we'll write some native JavaScript. I'll create a new socket by saying const socket is equal to new WebSocket, and we can provide a URL that's going to be ws://localhost 8080. So here, we're basically connecting to our local machine. Now I'll hold the shift key and then press enter a couple of times to get some spacing. And then we want to listen to the broadcast. So I'll say socket.onMessage is equal to, we get access to the event, and then we can open up a new function block. And within this function block, I'll simply run console.log and say message from server. And then we will console log the actual event data. So I'll say event.data. Perfect. I'll also put this right here so it's indented properly, even when we're typing in the browser. And finally, you can send a test shout once the tunnel is open by saying socket.onOpen is equal to, we're going to open up a new function block. I don't think you've anticipated that in this video, we're going to write JavaScript within the browser console, right? And then you can say socket.send, and you can say hello from the Chrome console. So this is going to be our first client that is connected to our WebSocket server. I think you get where I'm going with this. Our backend is actually running or acting as the WebSocket server, but then the browser will act as the client connecting to it. Make sure that you typed out all of this properly and that you didn't miss any ending string signs, and then go ahead and run it. It looks like I missed one ending parenthesis, so let's go ahead and fix that. It is missing right here. You might have caught that. And then go ahead and press enter. You'll see message from server, server broadcast, hello from the Chrome console. Now, the browser's native WebSocket API is globally available. As long as your server is running on localhost 8080, any tab in your browser can talk to it. So now if you go back to your terminal, you'll see a client connection. Yep, here it is, and a message from the client. Since I console logged the raw data, you can just see this binary buffer right here. But this is not a good way to check whether a WebSocket server is active. Some sites might block you, and you shouldn't be typing any code manually within your console anyway. It's just a simple hack and a reminder that any browser can run any kind of JavaScript. But a more proper way to test this out is through a terminal. Real devs love a CLI. Who doesn't? So there's a tool called WSCat that is basically curl, but for WebSockets. You can install it globally by running npm install-g wscat. I'll do it right here within a new terminal, and you might need to type sudo before to give your terminal permissions to be able to install it. Once installed, you can just run it by typing wscat-c and then type in the address to your server. Once you press enter, you'll be able to see that it says connected. Still, I want to be able to see both our server and the client at the same time, so I've closed the previous terminals, and I'll just immediately split them. That way, we'll have our own running by running npm run dev right here, and we'll have this new one that we just recently ran using wscat CLI. So now it says connected. Now, as soon as you type a message right here, something like, hey from WSCat with a smiley face, and you hit enter, you'll see the server broadcasted back to you instantly. And this is how you test the connectivity without a browser UI getting in your way. And then you can see that the server broadcasted it back. Now you can continue sending messages, something like hi, testing, test, test, and you can see that this is indeed happening in real time. You can even see that when I use the word test and then test test, the first part of it, like these characters, are the same. So later on, when we actually decipher it, it'll convey the right data. But if you're building a production API, use a tool like Postman. Most people think Postman is only good for REST APIs, but it also has a dedicated WebSocket request mode. So testing with WSCat is cool, but if you want to see the broadcast in action, you need multiple windows to talk to each other because that's where the magic happens. So finally, let me show you the coolest way to actually see your WebSocket server in action. By the way, see how it says client disconnected right here? And then we can easily reconnect if we want to. Yeah, so let me show you the coolest way. You can create a new index.html file within the same directory where we were on. In this case, we don't even have to use React or Vue. We'll use raw web APIs. I haven't written an HTML5 template in such a long time. But yeah, just create a simple doc type, a head, and a body. We can give it a title of WebSocket Live Test Rig. We can also insert some styles right here below the title by targeting the body and changing the font family to sans serif. It feels super weird to write CSS by hand. We're going to add padding of 20 pixels and a background of something like #121212, as well as a color of the text to something like #FFF. We can also target the ID of log, which we'll add soon enough to be able to send messages. And I'll set that to be background of #000, a padding of 10 pixels, as well as a height of 300 pixels. And finally, overflow-y of scroll, a border of 1 pixel solid #333 for the color. I know this is a testing app, but I still want to make it look nice. So if you right-click the index.html file, most likely your IDE or web editor will try to open it up for you in the browser, or conveniently, WebStorm automatically offers that right here. And I think I can even open it up in a built-in preview. Yep, that works. That's pretty cool. So let's see what we're building. I'm also going to continue writing the styles for the status-on class with a color of #00FF00. And then I'll add the status off, which is going to be #FF0000. Perfect. Just so we have some colors. Now let's actually create the HTML of this simple application. I'll start with creating a single H1 that'll say WebSocket Broadcast Console. Then right below it, we'll do a p tag that'll have an ID of status and a class of status off, and it'll say connecting ... You can see it right here. Let's make it fit within a single view. And then finally, I'll also render a form. So right below the p tag, you can render a form that has an ID of message form. Then it'll have an input with an ID of message input with a type of text, a placeholder of send cargo, and a require tag. Below it, we'll also render a button with a type submit, and it's going to say deploy message. And finally, don't forget to close the form component. Finally, below the form, I'll also render an H3 that's going to say live stream logs so we can track what's happening. And then I'll add a pre-tag with an ID of log where we can basically see the messages coming in. And now it's all up to us actually using the WebSocket, but this time on the client side. So right below the body, I'll create a new script tag. We won't be using any baked-in Socket.io script. Rather, we're going to build it ourselves by connecting to the base library. First things first, you have to get access to some HTML elements so that we can actually change them to see something changing on the screen once we receive the data from WebSockets. So get the status element by saying document.getElement by ID status, log by getting the log, and then input by getting the message input. But do you actually remember how to connect to a WebSocket? I mean, we talked about it within the crash course part. The step number 1 is to initiate the handshake. Sounds ominous, but basically the only thing you have to do is say const socket is equal to new WebSocket, and then you have to say which one you want to connect to. That's going to be ws://localhost 8080. Same thing that we've done in the browser. The moment this line executes, The browser creates a TCP connection to the server, sends an HTTP GET request with an upgrade WebSocket, and then waits for a 101 switch protocol's response. This does not mean the connection is ready, at least not yet. The socket exists immediately, but it is not usable until the open event fires. So let's say socket.add event listener, and we're going to add the event listener for the open state. We're going to have a callback function, and we want to change the status of the HTML element by saying status l.text content. We're going to switch it over to connected, and we'll say which port we're connected to, just like this. Then right below it, I'll also change the status element dot class name by turning the status to on. And now we want to create a utility function to prepend the log messages. We prepend instead of append, so the new messages stay on top for readability. So say const append log is equal to a function that takes in a label and a message, and we can create a new entry to our log. This entry will consist of a new date, so we know when the message was sent, to locale time string, and then finally after that we want to display a label. And we can add the \n character for a new line. Finally, we want to change the text content of that log, so log.textContent is going to be equal to the entry plus log.textContent. We're prepending it for faster reading. And now we can use this function, append log, to, well, append new messages. We're going to use it also within our event listeners, specifically for the open event listener, by appending a new log, which is going to be, in this case, of a type system, right? Because something is happening, the socket is being opened, and we're going to say something like tunnel established. Then we also want to add another event listener, this time for close. And this one is going to be super similar to this one. So we'll just copy its contents. And instead of connected, this time I'll say disconnected. And I'll change the status to status off. And the system will say tunnel collapsed. But why did we use add event listener instead of socket.onOpen or socket.onClose? Both works, but add event listeners allows for multiple listeners, and socket.onSomething only allows for one. In real application with logging and analytics and UI updates, you often want multiple independent reactions on the same web event. And why do we have events at all? Well, that's because WebSockets are event-driven, not request-driven. I mean, that's the whole point. You do not check for messages. The browser pushes events into your code. Specifically, the open event is fired only once when the HTTP WebSocket upgrade succeeds. The protocol is then officially switched and the tunnel is established. This is the first safe moment to call socket.send. When it comes to the closed, this is fired when the server intentionally closes the connection, or when the network drops, or when the socket.close is called. Once closed, the socket is dead and it can never be reopened again. You must create a new WebSocket instance. So now that we know about this, we can create a final event listener, the one for listening to messages. That's going to be socket.add event listener for the message where we get access to the event, and we'll simply say append log. This time it's not system, it's something like received. And here we want to display the event.data. This event is fired every time the server pushes data to the client. But do note that the client does not ask for messages. The server decides when messages arrive. And event.data can be a string, most common, like usually JSON, and it can also be a blob or an array buffer. In this demo, we're going to assume that it is text. Now, if you've been paying close attention to the right side, you'll see that we've gotten a system message. This can either be an open or a close. But we didn't get this additional message, whether the tunnel has been established or whether it collapsed. I think that's because I forgot to accept that second part of the message within the append log utility function. So if you head over here, you'll notice that right now we're just displaying the log text content to be equal to entry plus log.text content. But I'm not actually adding a message to this entry string. So right after the label, before a new line, we also want to display the message part right here. So now we can see message tunnel collapsed. Okay, now let's focus on sending and receiving data. Below all of these sockets, you can say document.getElement by ID, and specifically want to get the message form. Once you get it, we want to append an event listener to it, specifically the submit event listener that gets access to the event. Then we want to prevent default to not reload the page. And then we have to make a check to not try to send if the socket is dead. So I'll say if socket.readyState is not equal to WebSocket, which you have to import, .OpenState. In that case, we will append a new log that will say something along the lines of error, and then the message that we'll send is no active tunnel found. But if we do have it right below the if, I'll say const msg, as in message, is equal to input.value.trim, and then we can use the socket to finally send the raw message through the tunnel, and we can log that out by saying append log, where we can say sent, and then we'll say which message we actually sent through the tunnel, and then we'll reset the input value by setting it to an empty string. This is our little WebSocket broadcast console application that should show you in real time and in practice how WebSockets really work by having access to an active and running WebSocket server. Make sure that you're running npm run dev so it's live on localhost 8080. And once it is, you might need to close and then reopen the WebSocket. There you go. You can now see connected to WS localhost 8080, and you can actually send a message. Again, while we were building it, it was super useful to have this open in a built-in preview within WebStorm. But now I want to do something different. I want to open up a couple of these windows side by side. So once you open it up within your browser, go ahead and open another one and another one, and then put them side by side. That'll look something like this. We're connected in all three places, and now you can send a message from the window A. Let's type something like hello from window A and deploy it. Immediately, you can see a received server broadcast hello from window A coming up to screens B and C. And of course, since we're sending to all clients, we also received it back within window A. All of this is happening in less than 10 milliseconds. It is instantaneous, and we can actually speak to each other. Pretty cool, right? Believe it or not, you just developed a local chat application by using native WebSockets. Congrats. Sure, you can't chat with a friend yet, but this is a step in the right direction. And just a bit of theory, remember how you wondered how the server runs without Express? Look at the client now. There is no HTTP fetches anywhere. There is no request and response cycle. Once that open log appears, the HTTP protocol has been deleted from memory, and you're now communicating through a persistent TCP stream. If you look at a network tab, let's open it up right here. I'll go to network and I'll make it take a bit more space. You'll notice that there's some requests happening right here. And there is that localhost switch 101 status that I was telling you about. Now, there aren't dozens of requests, right? And even if you keep sending messages, nothing is going to happen on the network side, which is absolutely crazy because we are actually receiving new messages in the browser. But instead, there's only one single request that says pending. That's the one that switched the protocol and opened the tunnel for all the incoming messages. So give yourself a huge pat on the back. Or if you need me to say it, congrats, you really deserve that. You've just successfully learned how to implement WebSockets. But this is definitely not the end. Later, in JavaScript mastery style, during the build and deploy part of this course, you'll actually implement a WebSocket in an Express.js application and connect it to a React application on the client side. But just before that, I gotta tell you a few more things about different ways in how we can send data through the tunnel. So let's quickly go through that next. In the last lesson, you opened a persistent tunnel between the client and the server. You proved you can send data through it. But in production, sending data is the easy part. The real skill is designing message flow. Because the moment you write socket.send hello, you're sending a blind packet. The server receives it and has zero context. Is this about a chat message, a typing event, a command, or a delete request? It has no idea. So we fix that with structure. Welcome the envelope pattern. It's a must for real apps. Because in real-time apps, you don't send raw strings. You send a message envelope that includes intent. Think of it like shipping a package. You don't just drop an object into the mail. You label it. Let me give you an example of a clean WebSocket envelope. You define a type, such as a chat message. You give it an ID, maybe some metadata, and most importantly, the payload. That includes the text of a message you want to send and the ID of the room you want to send that message to. There are a couple of important parts here, but it's super simple to understand. The type tells your server what logic to run. The ID lets you track the message. The payload is the actual data. And then there's metadata, which includes the optional context. Now your server becomes a switchboard. It looks only at one field and instantly routes the action. So as soon as you parse the message, you open up a literal switch statement in JavaScript, check out the type, and then depending on whether it's a message, a typing status, or a request to join a room, you can immediately handle that within your application. Clean, scalable, and production ready. Now, there are two ways to structure envelopes. The first one, and the one I actually recommend, are type-based commands. This is best when your app has a known list of actions, such as chat message, typing, user join, and more. It's perfect for chat apps, dashboards, and collaborative tools. But there are also topic-based messages, pub/sub style. This is best when channels are dynamic. For example, you can send a topic of stock Apple with the data containing its price, or the topic of a game happening between Lakers and Warriors with a specific score. This is perfect for sensors, tickers, live markets, and sport engines. And yeah, as I told you before, once the structure is solved, you have to choose the format. There's JSON and binary. JSON is the default, easy, readable, debuggable, flexible, and for most apps, JSON is the best choice. But binary is what you want to use when messages are of a high frequency. GPS updates, mouse movements, audio chunks, game states. Instead of sending readable text, you send raw bytes because it takes less bandwidth and less latency. And believe it or not, most serious apps actually use both. JSON for control messages, join, auth commands, and binary for high-speed data. But when you make that connection, and when you decide in which format you want to send it, we have to move from message structure to message routing. Because in that WebSocket that we implemented before, you're basically shouting messages to everyone. Production apps don't do that. So there are a couple of different patterns in which you can send messages. There's broadcast, unicast, and multicast. Broadcast is also known as one-to-all. This is like the megaphone pattern. One message goes to every single connected client. It has its uses for things like systems announcements, global alerts, or service status updates. Just remember, 10,000 users means 10,000 cents. That's fine occasionally, but not fine every 100 milliseconds. The second pattern is unicast, or one-to-one. This is a DM. Only one person gets the message. To do this properly, you keep a registry where you connect a specific user ID to a socket, because without that, you'd be looping through every client just to find one. With a map, lookup is instant. You want to use unicast for private messages, user notifications, or admin actions. And finally, there's multicast, or one-to-many, often used to send messages to specific rooms. It's a group chat pattern. You don't send to everyone, you only send to a specific room. Use it for Discord channels, game lobbies, live event chats, and collaborative documents. Because rooms are the difference between everyone hears everything and only the right people hear the right thing. And we also have to talk about acknowledgements. Because here's the brutal truth. WebSockets are fast, but they're also a fire and forget. Unlike HTTP, there's no automatic 200 OK. So for critical actions, you add ACKs or acknowledgements. You send the message with an ID, the server processes it, and replies with the same ID as a receipt. If the client doesn't get the receipt in time, retry. That's how you add reliability on top of WebSockets. And another pattern I want to teach you is the pub/sub pattern. Pub/sub is like subscribing to a newspaper. You only receive what you actually care about. For example, user A subscribes to Apple stock, B to Google, and C again to Apple. So when Apple stock updates, only A and C get the updates. That's pub/sub. But the real challenge is scaling, because when you have multiple servers, each server only knows its own clients. So if server 1 publishes an update, server 2 won't know about it. That's why real systems use a message broker like Redis. The broker becomes the central broadcast layer between all servers. And that's how you scale to millions of connections. So now you've really leveled up. You're not just sending messages, you're designing flows with structured envelopes, targeted routing, you're checking for reliability with acknowledgements, and you can even scale with the pub/sub pattern. But now the big question is, when should you actually use WebSockets? And what kind of data should go through them? At this point, you might be thinking, okay, WebSockets are real time. So if I want to build the next Zoom or Netflix, do I just use more WebSockets? And the answer is yes and no. WebSockets are powerful, but they're not a silver bullet. If you try to push 4K video through WebSockets, your server bill will explode and your servers will get lag. So let's zoom out a bit and map the real-time world. Let's start by talking about WebRTC for voice, video, and P2P. So far, everything we discussed looks like this: client, server, client. And that's perfect for chat, notifications, collaboration, and dashboards. But for heavy media, like video calls, routing everything through your server is expensive and slower. And that's where WebRTC comes in. WebRTC lets two browsers talk directly, peer-to-peer, with ultra-low latency. And that's perfect for audio and video. The only catch is that WebRTC needs a matchmaking phase. The two browsers need a way to find each other and exchange connection information. That step is called signaling, and signaling is usually done with WebSockets. So the flow will look like this. Client A connects to a WebSocket server. It sends an offer for client B. Client B replies with an answer, and once they've exchanged network details, WebRTC connects them directly, peer-to-peer. The server steps out, the media flows directly, and that's exactly why apps like Zoom use WebSockets for signaling, chat, and join events, but then WebRTC for audio and video streaming. Now, besides WebRTC, there's also Web Transport for ultra-low latency streaming. Because what if peer-to-peer isn't possible, but you still need extremely low latency? I'm talking high frames per second cloud gaming, live media pipelines, and competitive real-time systems. WebSockets are built on TCP, one of the primary ways in which we transmit data on the internet. But TCP has a big downside. If one packet gets lost, everything pauses until it's resent. That's called head of line blocking. Web Transport fixes this by using HTTP3, powered by Quick. So instead of one stream that can freeze, it supports multiple independent streams over a single connection. So if one stream gets delayed, the others keep moving. That means fewer freezes and smoother real-time delivery. But unless you're building something insanely latency sensitive, you should still stick with WebSockets. They're stable, supported everywhere, and battle tested. And finally, there are SSEs, the server sent events. Because sometimes, even WebSockets are actually overkill. If your app only needs one-way updates, like stock prices, news feeds, and live dashboards, then SSE is a cleaner tool. It's basically server pushes updates and the client listens. No two-way messaging, no full duplex tunnel, just a one-way stream over HTTP. Lightweight, simple, and it reconnects automatically. So when do you use what? Well, here's the cheat sheet. WebSockets. Two-way, real-time apps. Think chat, collaboration, dashboards. WebRTC, great for heavy media, peer-to-peer. Voice calls, video calls, and file transfers. Web Transport for ultra-low latency streaming, high-performance real-time systems. And SSEs, or server-sent events, for one-way server updates. Think stock tickers, feeds, and streaming data. And if you're still unsure, just use this one simple rule. Does the server need to push updates? If yes, then SSE or WebSocket. Does the client need to talk back? Then WebSockets. And are we talking about sending heavy audio, video, or huge data? If yes, then WebRTC. You now have the full map of the real-time world. So let's recap the journey. You first learned about why HTTP polling is wasteful and how WebSockets create a persistent, full duplex tunnel through the handshake process. Then you learned the architecture of WebSocket connections, lifecycle stages, ping-pong heartbeats, ghost connections, and how data flows through opcodes. You then built your first WebSocket server with the WS library, tested it with WSCat and a browser, and saw real-time broadcasting in action. In Lesson 4, you learned how to structure messages with the envelope pattern, when to use binary versus JSON, and the 3 core communication patterns such as broadcast, unicast, and multicast. And finally, you learned that while WebSockets are powerful, they're not the only tool. Instead, you know when to switch over to some other tools, such as WebRTC for peer-to-peer media, Web Transport for ultra-low latency, and SSEs for one-way data feeds. The crash course is complete. You understand the theory, the architecture, and the ecosystem. Now, it's time to build something real. In the Build and Deploy section coming up next, you're going to build a production-grade live sports scoreboard with WebSockets for real-time score updates, Express for the backend API, Postgres for data persistence, a React frontend that updates in real time, and proper error handling with the reconnection logic and state management. And here's the truth. Just coding WebSockets and shipping a production-grade real-time app are 2 completely different games. Because building it locally is only like 20% of the battle. The other 80% is making sure your app survives the real world. Attacks, traffic spikes, crashes, monitoring, deployment, and code quality. Most tutorials just stop at the happy path, but not this one. That's why I've partnered with the best tools that'll help you make the most out of WebSockets in production. The first one on the list is CodeRabbit, and it's all about code quality. See, real-time apps are easy to break. One missed edge case and your server starts behaving weird under load. That's why in this course, I'll also teach you how to use CodeRabbit. It's an AI-powered code reviewer that helps you catch issues early before they hit production. And that's more important now than ever before since we generate a lot of code using AI. And their team recently did some research and it showed that AI PRs had 1.7 times more issues overall. So in this course, I'll show you how I use CodeRabbit as we continue building the app. You can get it for free by using a special link down in the description. Next, we dive into security with Arcjet. Right now, your WebSocket server is basically wide open. Someone can connect 10,000 times from a single IP, spam garbage data, or stress your server until it falls over. And traditional security tools aren't designed for persistent WebSocket connections. That's why later in the course, I'll also teach you how to use Arcjet. It helps you protect your apps, including real-time WebSocket connections, with rate limiting for connections and messages, bot detection, and attack and abuse prevention built for real-time APIs. Click the link in the description and create a free account. You'll see exactly how I integrate Arcjet inside the sports scoreboard project that's coming up next. Now, you'll also need visibility. If your memory starts creeping up, or your latency spikes, or if your database maxes out, you want to know before your users do. That's why I'll also teach you how to use Site 24/7. It gives you uptime monitoring, alerts, and performance dashboards so you can track your server health, WebSocket connection counts, and real-time latency. So instead of guessing, you're engineering proactively. All right, you're now set to build and deploy a production-grade real-time system. And once you build this with raw WebSockets, learning Socket.io will take you like 10 minutes. Socket.io is just a library that automates everything you're about to build manually, like reconnections, rooms, acknowledgements, and fallbacks. But because you'll understand how it all works under the hood, you'll be able to read the Socket.io docs and immediately know what every feature is doing and why. So in this course, you're not just learning WebSockets, you're becoming a real-time systems architect. Now, let's build something real. Before we write a single line of WebSocket code, check out the final boss, the real-time app you'll engineer. It's called Sports, a high-level professional-grade backend that powers a live sports dashboard. It's a living system built to handle raw data flow, security, and thousands of concurrent fans screaming for updates. The second a user hits the site, your backend does a dual action handshake. It fires off a REST response to populate the match list while simultaneously upgrading the connection to a persistent WebSocket. You're going to implement this welcome logic and the background heartbeat pings that big players like ESPN use to keep millions of connections alive. If that pipe drops, the experience dies. You're going to make sure it doesn't. Next, and this is where it gets powerful, you're building the automated match discovery. Your API will be optimized for background polling, allowing the system to detect new games the millisecond they're committed to the database. This means that your users will see the updates immediately without ever touching the refresh button. Now, building on instant updates, we have to talk about efficiency. In a high-traffic environment, broadcasting every update to every user is a one-way ticket to a server crash. That's why you're going to engineer a selective subscription model. Your WebSocket server will wait for a specific subscribe command before it starts streaming match-specific data. This will not only keep your backend efficient, but it'll push the scores and commentaries only to the users who are actually tuned in. So once the user is subscribed, the real-time engine starts. So when a goal hits the database, you won't just send a generic alert. You're going to broadcast that targeted score update and commentary events packed with different timestamps and metadata. Your backend will start providing the exact data the UI needs to highlight that game-changing moment the instant it happens. Finally, we have to protect the entire application. So you'll build logic that auto-kills data streams when a match ends and handles all the disconnects properly. Most importantly, you're wrapping the whole thing in a security shield to keep bots and spam out of your pipes, thanks to Arcjet. This is the exact hybrid architecture, REST for the foundation and WebSockets for the speed, used by the fastest platform on the planet. You're moving beyond the basic sites and learning to engineer a system that handles data like a pro sports network. It's a massive skill to have this in this AI era, and you're gonna master it step by step. In the crash course, you learned WebSockets, what they are, how they work, common architectural patterns, real-time data flow, and now we're about to build a live sports app that updates instantly. But there's one part that almost nobody teaches properly: deployment. Because building WebSockets locally is pretty straightforward, but shipping them in production is where most apps break. What happens when 1,000 users connect all at once, and those connections stay open for hours? Real-time systems don't behave like normal REST APIs. They need to be stable and predictable. And this is where many popular platforms start to struggle. Some platforms are optimized for serverless or short-lived requests, which can introduce issues like cold starts, sleeping instances, connection limits, usage caps. That's why today's video is sponsored by Hostinger. As of recently, they offer fully managed Node.js hosting, which gives you an always-on runtime built for long-lived connections, exactly what we need here, without forcing you into serverless constraints, or turning this into a full-blown DevOps project. You can deploy straight from GitHub, your framework is auto-detected, SSL is handled automatically, and your app stays live with huge reliability, supporting stacks like React, Next, and Vue, but most importantly, Express, Nest, and real-time backends like the one you're going to build in this video. That's why I want to teach you real-world deployment with proper Git commits, domain setup, HTTPS by default, and monitoring without any issues. And since you're a JS Mastery subscriber, Hostinger is offering you a limited time discount. Click the link down in the description and click View Plans. Even though the Cloud Startup plan is super powerful, Business Plan is going to be more than enough for us, allowing you to host 5 managed Node.js applications. So choose this plan. And if you're serious about backend development, I would recommend choosing more than 12 months because then you're going to get a free domain name. And don't forget to enter the JavaScript Mastery coupon code for an additional discount on this offer. Great, you can buy it now and then we'll use it later on once we develop our application. Once you buy it, you'll be able to choose your domain name, which you can do right away, or for now you can use a temporary domain. And then the recommended way to set up our app is to import a Git repository. So go ahead and connect with GitHub. You can connect it to your personal one and give it access and authorize. Once that is done, at the end of this build, you'll be able to find your repo and deploy it right here with a single click. For now, we can just exit the onboarding, and then we'll be back to set it up at the end of this course. With that in mind, let's dive right into the action and let me teach you how to use WebSockets within real-time production applications. Let's dive right into the build by opening our code editor or IDE. My preferred choice is WebStorm. As of recently, WebStorm became completely free for non-commercial use, which means that you can now access this super powerful and professional JavaScript and TypeScript IDE. I'll leave the link down in the description so you can download it and follow along and see everything that I am seeing in this course. And another reason why I love WebStorm so much is because with it, you can also integrate Junie, your smart coding agent. Junie allows you to explain your task directly within your IDE, then it collects all the necessary context from the project you're working on, and then it can write the code or tests for you. And you can see that it works super well with WebStorm. So you can also download it for free right now. With that in mind, let's go ahead and create a new project or just create a new empty folder on your desktop and name it something like Sports, which is the name of our WebSocket application. Once you create it, it'll look something like this. And now the goal is to set up a new Node.js Express server. So open up your integrated terminal and run npm init-y to quickly initialize a new Node.js project. That'll essentially spin up a new package.json file. And first things first, we want to update the type from common.js two ES6 modules that support import and export statements, which we use a lot on the web. So I'll simply say type is equal to module. Then we want to install Express by running npm install express, which will simply add it to the dependency array right here within the package JSON. Express will allow us to very simply spin up a Node.js server. We also need a .getignore file, so create a new file in the root of your application called .getignore, because later on I'll show you how you can also deploy this project, and it's important that you don't deploy any environment variables. Now, if you Google for a collection of useful .getignore templates, you'll be able to find this GitHub repo where you can find a special node getignore, which contains the most common things you don't want to push over to GitHub. So you can simply copy it and then paste it right here. The next step is to create a new folder called source, src. This is where we want to have our entire server. And then within it, the starting point of our server called index.js. Now the goal is to set up the Express server right here by saying import Express from Express and then starting a new app. But since you most likely already know how to set up a simple server, I want to use this opportunity to improve your productivity using AI tools, not to think for you, but to help you generate some stuff that you already know. So in this case, I'll be using Junie. You can get to it by heading over to Command-Shift-B and searching for plugins and then installing that plugin, or just pressing Control or Command-Shift-B and then typing Junie. This will pull it up right here on the right side, and we're ready to get started. So let me show you how I use AI to help me develop these projects. We can say something like set up a simple express.js server in JavaScript that listens on port 8000, uses JSON middleware, has root get route that returns a short message, and logs URL when the server starts. It cannot be any simpler than that, and this is exactly what we need to spin up a simple server. So let's go ahead and run it. You'll see that Junie will now read our request, take a look at the context, which there isn't a lot of it right now, but there will be soon, and then it'll create a plan, and it'll keep us updated on the task progress. So you can see right here that it already created a simple server, and sometimes it's going to ask you to run some commands to verify that it did the job properly. I gave it access to run that command, and you can see that now it knows that the Express server started successfully and responded with a greeting message. So it even checked its work. With that in mind, we now have a simple Express server right here, 15 lines of code that includes the port that we're listening on, the middleware, so we can read JSON context. Then we have the first root route, and then we have the logging to let us know that we're actually live. Pretty straightforward, right? You can open up the terminal, and before we run any kind of code in there, let's add some scripts within our package.json by deleting the test script and instead adding a dev script that'll run node --watch source /index.js, as well as a start script, which will run node source /index.js without the watch script. The watch will actually keep track of changes as we continue to develop this application. So now you can simply run your server by running npm run dev, and you'll be able to see that the server is running on localhost 8000, which you can open up within your browser. Hello from Express Server. This was a smooth start, but from the start, I want to teach you the good habits of coding in general, and that is to always initialize a GitHub repo from the start. Not later on when something goes wrong, but before it does. So head back over to GitHub, and at the top right, you'll be able to create a new repository. You can do it on your personal profile, and you can name it something like sports. I'll also add -WebSockets so that everybody knows what this project is all about. You can skip everything else and simply create a repo. Now we need to run the following commands. So let's do it one by one. I'll open up a new terminal. I'll keep this one running and rename it to app, but the second one will simply rename to terminal so we can continue running additional commands while our server is running. You can run git init, git add dot, git commit -m, init, Then we'll have to do git branch-m main to switch over to the main branch, git remote add origin and connect it to your remote URL, and finally git push u origin main. Within seconds, this will push your server to the web. Now, what I always like to teach on jsmastery.com whenever we're working on some courses is that you tidy up your repos. No matter how big or small the projects are, you're adding all of them to your profile. So if somebody's checking it out later on, you want to make sure to make it presentable. So add a nice README. You can take a look at how I tidied up mine after the video and then do it, but also press this little settings icon, and then you can hide the releases, packages, and deployments. Add some kind of a description saying Express and Postgres demo for live match commentary with a WebSocket broadcast channel. That's going to be enough. You can add the link to your deployed application. You'll have this later on as soon as we deploy it, because I'll teach you how to do that too. And then you can add some relevant topics such as WebSocket, WebSockets, maybe WS library, and so on. Now go ahead and save changes. And it already looks much better. Of course, it'll look even better once you add the README. But for now, this is all that we need. Perfect. You now have a clean Node.js and Express server running locally with proper scripts, a solid folder structure, and your repo initialized. So the foundation is set. Next, we need something real-time apps can't live without, and that is a database. Because WebSockets don't create data, they broadcast it. So in the next lesson, we're going to design the database schema for sports and set up Postgres using Neon and Drizzle. Let's do it. Before we go real time, we need something worth sending in real time, because WebSockets don't magically create data, they only move it faster. And if your data model is messy, your real-time system becomes messy too. Here's the rule. The database is your source of record. WebSockets are just your distribution layer. So in this lesson, we're designing the foundation of sports, what a match looks like, how we store score and status, and how we represent the live story of the game through commentary events. And this is where most developers mess up. They jump straight to sockets, start broadcasting random JSON, and 2 lessons later, they realize, wait, how do we persist this? How do we rebuild state when a user refreshes? How do we handle multiple servers? And how do we avoid sending fake or inconsistent data? That's why we're doing the schema now, because once our schema is solid, every WebSocket becomes clean, structured, and reliable. Okay, so let's build the database layer properly. For data persistence in this application, we'll use Postgres. Specifically, we'll use Neon Postgres. They recently got this site redesigned, and I gotta say, it's looking amazing. So simply head over to read the docs, and then search for Drizzle, and then you'll find this doc that says connect from Drizzle to Neon. Right at the top, you'll see a pre-built prompt for connecting Node TypeScript applications to Neon using Drizzle ORM. And nowadays, when I'm installing services, I like seeing this. So go ahead and copy the prompt. Similar to how we got this simple Express server set up by Junie, we can give Junie the prompt we just copied over from Neon. So go ahead and run it by pressing Command-Shift-P and then opening Junie. And we'll give it a new task by simply pasting what we just copied. Notice that it says that we want to integrate it with TypeScript. To keep this application specific to WebSockets, I didn't want to bloat it with additional types. So in this case, we're going to keep it just JavaScript specific. You might have to change this word a couple of times whenever TypeScript appears, just to not confuse it. Yep, it's definitely showing up a few times. Try to replace as many as you can see. And in case we miss some, I'll say it is possible that this prompt will use the .ts extensions, but I decided to proceed with JavaScript, so please do that instead. No TypeScript in this case, and run it. Now, this is a larger prompt, so let's see how Junie handles it. In some situations where Junie thinks that it might need some additional input from you, it's actually going to proceed and ask you. And this is what I love about it. When you give it a prompt, it's not just going to go ahead and do it, even though it might be wrong, but rather it's going to ask you a question. Question is about choosing the preferred driver and drizzle adapter. In this case, since we're using it on the backend setup, we want to go with Node Postgres, the classic, stable, and mature driver for Node.js. So you can simply type it right here and press enter. Now it'll ask you to run some commands, such as the one to install all the necessary dependencies and dev dependencies. So I'll let it do that. There we go. It started by creating a .env file that'll contain our database connection string, and it's editing the drizzle config, the schema, and the db.js file, and finally it'll include all the changes within our index.js. Of course, we'll go through all of these created files together just to verify that they're good. Finally, it's updating us on task progress, and it says the project is now ready for the user to add their connection string and run migrations. Perfect. Let's go ahead and check it out. Our index.js remained the same. Then we can check this CRUD demo. I'm not even sure whether we asked it to do that. In this case, we'll do everything from scratch. So I will simply remove this part and we'll do it together. Then within the db.js file, you'll see that we are importing .env config so we can actually process our database URL. We're importing drizzle from Node Postgres and PG. We're creating a new pool and hooking up to our database. Make sure this file is within the source folder, and I'll actually put it within another folder called db so it's more nicely structured as the application grows. Then we'll also move this schema file inside of the database as well, as it's all about the database. And in the schema, it created a dummy demo user stable, which for now I will remove, and I'll show you how we can add our own data later on. Finally, head over into drizzle config, where you'll see that it's going to ask about our database URL, and then it'll try to connect to our schema, which is under source, but since we moved it, we have to say source db schema.js, and the rest can remain the same, but don't forget that we actually have to add this database URL, which for now is a fake connection string, but we need to get a real one coming from project dashboard connect. So if you head over to the documentation page we were on, and head over to Neon Projects, you can log in. Once you're here, create a new project, give it a project name, something like sports, and click create. Then you can click connect and copy the connection string. Once you do that, you can head back over to your .env and simply override the current one. That's going to be PostgreSQL, NeonDB owner, and then your password. Next, it's time to define schemas for this application, which is all about deciding what to store and how to store it. But building a database for something that happens in real time, like a buzzer beater shot or a last-minute goal, is all about figuring out what stays still and what moves fast. So before you worry about any action, you need a place to hang all the data. If you're building this, the first thing you create is the match, which acts as your anchor. You group together the stuff that is true for the whole game, such as who is playing, what the sport is, and when it is supposed to start. You might ask, should I just store the team names and leave it at that? Well, not quite. You also have to think about a specific status field, which gives your app a way to filter out the noise of which match is live, scheduled, or finished. So your backend can then just say, only show me the live games and ignore the rest. Next, you have to think about the score. Every sport has to have a score. So where do we put the score? You might think about calculating it on the fly by looking at every goal ever scored, but that'll only slow you down as you have to calculate every time you want to display the score. That's why you can create two separate fields, home score and away score, right there to store the score of both teams. Then, once the match is set, you need to handle the story of the game. You can call this commentary or events stream. Whatever it is, this is where the real-time magic happens. The first thing you'll wonder is, how do I make one table work for every sport? Because if you make a column called wickets, which is used for cricket, and a column for touchdowns, which is all about American football, then your database will become a messy, giant spreadsheet with mostly empty holes. Instead, you design for events. You just need a few generic buckets, such as who did it, that is the actor, what happened, which is the message, and when did it happen. But then when it comes to specifics, like how fast was the ball moving, well, this is where you can use the JSON column. It's basically a digital junk drawer that's actually useful. You don't have to change your database structure every time you add a new sport. You just throw those extra details into the JSON bucket and let the frontend figure out how to display it. And that's how you define your database schema, taking one step at a time, asking the right questions, and then answer them to form your database structure. So now that you know how your database schema will look like, let's use AI to generate them. Back within our application, open up Junie or your AI agent of choice, and you'll be able to paste a prompt that I'm gonna give to you in the description down below. Head over to the video kit, open it up, and you'll find a prompt to generate schemas. Let's go through it together. Act as a senior software architect. Generate a source DB schema.js file using Drizzle ORM and Postgres for a real-time sports application. Create a match status enum with values scheduled, live, and finished. Create a matches table with fields, ID, sport, home team, away team, everything we just discussed. And then there's that commentary table for real-time data. There is also the metadata, which is going to contain all the additional information specific to, well, specific sports. And I'm just telling it to use camel case for variable names. Let's do it. Let's see if it'll have any questions for us or if we were pretty clear on our request. There we go. It looks like it's starting to do it by updating the task progress. And it's asking us whether we immediately want to run db generate. For now, I'll skip it. I'll walk you through that manually once we actually check out the schema. But this is nice because Postgres doesn't understand Drizzle schemas. So running this command will actually generate corresponding SQL code to be able to recognize it. But for now, I'll skip. There we go. The changes were implemented all within a single file called schema.js. There are only two different tables. Again, this is just code, a lot of manual code that you would have to write. But if you, instead of writing, spend time thinking about it like an architect, then somebody else can do the writing for you. But again, it's important to think beforehand. That's how I want you to use AI in the future. So let's go through these together. We have the match status enum, which can either be scheduled, live, or finished. And we're using this later on when we discuss the status. Then we have an ID, which is the primary key. And we also have a type of the sport, the home team and away team names, the status, the start time, end time, home score, away score, and created at. And similarly for the commentary, we have same things that I've showed you on that diagram not that long ago, which contains the minute when something happened, which match does it belongs to. This is important. This is the reference to the matches table, and it has all additional information. So now we have to head over to package.json, and you can see that Junie also generated these scripts for us. db generate, db migrate, and db studio. These are necessary for us to be able to convert this nicely readable Drizzle code over to SQL. So let's go ahead and run these commands one by one. I'll head over to our terminal and run npm run db generate. This will create raw SQL instructions for setting up and modifying the database structure. And you can see it right here under Drizzle, and you can see how that looks like. But this won't just yet create your tables. That's because we've never conveyed them over to Neon. To do that, you have to run something known as a migration command that lets it know to apply the generated SQL migration files over to your database. So run npm run db migrate. And again, make sure that you have that script right here within your package.json so you can actually run it. And press enter. You might be able to see some warnings or something, but if there are no big errors, you should be good to go. We can even verify that the table got created by heading over to our Neon dashboard and heading over to tables. Under tables, you should be able to see tables for matches and commentary. This means that you've just successfully set up our database, which is super important so that we can soon enough start focusing on what you came to this video for in the first place. And that's moving that data that we now have the structure for in real time. So now that we've architected the structure of our database, I think this deserves its own branch and a commit. So open up your terminal and run git checkout -b and enter the branch name. In this case, it can be feat, as in feature that we are adding, database-schema. This will switch you over to a new branch. Then run git add dot, git commit -m, implement database schemas, and run git push. Since you've created a new remote branch, you'll need to set the upstream to that branch on your remote repo. So simply copy this command that it gave you right here and press enter, and that'll push the changes to the new branch. Now you'll see that this branch had recent pushes a couple of seconds ago. So let's go ahead and compare it and open up a pull request. This is how the process looks like in any kind of a real-world environment when you're developing apps with teams. Or even when you're doing it yourself, but you're working on a serious project, this is how you want to do it. So go ahead and create a pull request, and I'll tell you specifically why this is super useful. See, this PR on its own wouldn't be super useful if you're checking it out yourself. Of course, if your mentor is reviewing it for you, that's great. But oftentimes, mentors have more important stuff to do. So what you can do to improve and to be a better developer is to get CodeRabbit to review this code for you. Because a bunny is never late, nor is he early. He reviews precisely what he means to. I mean, jokes aside, let's set up CodeRabbit so it reviews our PRs. I'll leave the CodeRabbit link down in the description, but essentially what it is, it's an AI code reviewer that cuts not only code review times, but also bugs in half instantly. And I actually want you to use it for a purpose that is not necessarily listed right here on the homepage. And that is for learning and improving your general code architecture understanding. See, CodeRabbit will sometimes point architecture things that I might have missed while developing it first time. Then I'll see what it suggested, I'll improve it, and I'll learn based off of it. So once you click the link down in the description, go ahead and try it for free. You can sign up using GitHub. And once you're in, you'll have to give it access to your repos. In this case, I believe it already has access to it. So if you search for sports, you'll see that it is there because I gave it access to all the repos within my organization and within my personal profile. So simply give it access to the repos. And then when you head back over to your PR, you'll be able to see that now we have a summary generated by CodeRabbit, as well as a walkthrough of what we did within this PR. You introduced Postgres database setup using Drizzle ORM. It includes the configuration files for Drizzle, schema definitions for matches and commentaries, and more. It even tells you what happened per file or per cohort of files. And later on, once we have more complex PRs, it'll give us diagrams to visualize the flows within our application. Oh, and here's something to think about. We architected the database, right? We thought of the different tables that we want to add and the fields that they're going to have. And then we told that to the AI. That's totally okay. That's a normal process of how web development works today. But recently, I came across this CodeRabbit review that found that AI code creates 1.7 times more problems. So while it's great for speeding up your workflow, sometimes little bugs are going to sneak through. And that's another one of the reasons why I love using CodeRabbit to give them a quick check. I'll leave this blog post in the description in case you want to give it a deeper read. With that in mind, since this PR was super simple, CodeRabbit didn't have anything to complain about. But we'll see whether that's still the case later on, once we start adding more business logic for our real-time sports application. Go ahead and merge this PR, and then back within our application, you'll want to navigate over back to the main branch and run git pull to pull all the latest changes we just merged. That means that we are ready for the next lesson. In the previous lesson, we've set up Drizzle and Neon, basically creating a solid home for every goal and game update. This database is our source of truth that makes sure that every game stays safe, even if a user refreshes their page. Now, we'll need to find a way to access this data. So we'll build REST API endpoints to get access to our matches. But at this point, you might be thinking, wait, I thought this is a WebSockets course. So why are we building a REST API first? That's a great question. Because in real production systems, WebSockets don't replace REST. They complement it. So here's the split. REST is for commands and initial state, and WebSockets are for live updates. Meaning, REST creates the match, REST fetches the list of matches, and REST is what you hit when you refresh the page or load the app for the first time. Then WebSockets take over. Match created, score updated, commentary added, live events pushed instantly. If you try to build a real app with only WebSockets, you end up reinventing REST, but worse. So in this lesson, we'll implement the matches endpoint, where we can create a match, list matches, and we're doing it with a proper validation using Zod. So our real-time assistant isn't just fast, but correct. Let's build a base API. Let's start by creating a new file for our router. You can do that by heading over to Source, create a new folder called Routes, and within Routes, create a new file called matches.js. And WebStorm even asks me to automatically add it to Git. This is super useful, so I'll click Add. Within here, we can first import router coming from Express, and then we can create a new router instance to handle all the match-related routes. Export const match router is equal to a new instance of router, and then you can say match router dot get. This is going to be the base route where we simply want to res that status of 200, and we'll send over a JSON object that'll contain a message said matches list. We now want to import this matches router within our source index.js right here below our current home route by saying app.use, and we want to use the specific match router, which you can automatically import at the top, and it's going to point to /matches route. So that means that this route right here, whatever you type, will start with /matches/ and then this domain. In this case, if you leave it empty, it's going to be just /matches. Also, make sure not to forget this app.use express JSON, because this is the line that enables middleware that enables Express to understand JSON data. Without it, you would not be able to read JSON sent from the front end or from Postman, for example. Next, we'll use Zod for all request body params validation. So you can install it by running npm install Zod. And again, if you want to check it out, Zod is TypeScript first schema validation for static types. It works even better with TypeScript, but it's even okay with JavaScript. And you can see that the main and only platinum sponsor right here is CodeRabbit. Super cool to see one great dev tool sponsor another, such as Zod. But yeah, in simple words, Zod will act as a middle layer between the raw user input and your application logic. So it'll make sure that the score that we pass in is actually a number rather than a string. Setting it up is highly repetitive because the rules usually mirror your database columns. So it's more efficient to use an AI to generate those standard validation patterns. So once again, I'll open up Junie and we'll give it another prompt right here. And of course, I prepared this prompt for you in the video kit link down in the description, so you can quickly add it here for yourself, and then we're going to go through it together. Generate a validation file using Zod at source validation matches.js that exactly follows these requirements. I mean, I'm being super precise and strict right here. Usually you don't have to be, you can just speak to it normally, but I just try to be super precise to make sure that both you and I get as similar output as possible, so you can follow throughout this course without any issues. Okay, so we wanted to create a list matches query schema that validates an optional limit as coerced positive integer with a maximum of 100. Create a constant named match status with key value pairs for scheduled, live, and finished. A create match schema that validates sport, home team, and away team as non-empty strings, and I think you get the idea. So let's go ahead and run it. And notice how I'm using AI occasionally, not to develop our entire application, but only within specific files at specific points in time when we just wanted to get some work done. Then, as you learn just how powerful it is, you can figure out exactly when you can and can't use it. You're the architect, AI agents are a tool. Sometimes it's going to ask me to give access to the terminal so that it can automatically create repositories for us. So you can see right here, it'll create a directory under source and call it validation. And within validation, it'll need to create a new file. And there we go. It created a new matches.js file, and it even created a test validation, which is super interesting to validate various schemas and constants related to match data. Now it wants to run that test. Sure, why not? It looks like most schemas passed, but the one that failed due to a type error is now getting fixed. It'll try to rerun it, and all schema validations have passed, and now it's going to say, I'm even going to remove this test file for you, so your code base remains clean. Wonderful. Now let's go over the validation matches.js file. First, we have an object that defines different match statuses, and then we have some helpers, like list matches query schema, where we specify the limit of matches. Same thing for some information about the match ID and match ID params, even some helpers for ISO date strings, and then we're using all of that within these Zod objects. The first one is used to validate the inputs that we passed into the create match, such as that the sport has to be a string with minimum characters of 1. Same thing for the home team, away team. The score has to be a number, so it'll automatically transform it into 1. It has to be non-negative and it's optional, and it's also going to add the time. Now that we have the validations, let's create another folder within the source folder and call it utils. Within utils, create a new file called match-status.js. Within it, we can create a quick utility function that's all about figuring out the match status. I've also generated this using Juni, and I'll provide this code within the video kit link down in the description. But essentially, you have two different functions right here. One, to get the match status. In simple terms, what it does is it checks the start time of the match. And if it's before now, we set it to scheduled. But if it is after the current time, then it is finished. And if it's neither of these two, then of course it is currently live. And now we want to implement the post request to actually create a new match. We can do this within routes matches.js, just below our current route. I'll do it by saying match router dot post. It's going to be on the / route, where we're going to have access to the request and the response. And from the frontend side, we'll send over all the data through request.body. So here we have to parse that data by saying parsed is equal to, and now we can use the create match schema and call a safe parse method and then pass the rec body. This will make sure that the body we're passing in matches our schema. Then if no parsed.success, in that case, we can just return a res.status of 400.json that'll contain the error saying invalid payload, and it'll also contain the details, which are going to be json.stringify parsed.error. So we can provide some additional information. Finally, if that is good, we can open up a new try and catch block. In the catch, we'll simply return a error with a status of 500, which means server error, with a JSON of error, failed to create match, and with the details set to json.stringify, and in this case, we can just use the error. But in the try, we can actually try to insert this new match into the database. So let's do it right here by saying const destructure the event that we will have created when we call await db.insert. Now, since we're using await here, we have to add async at the top of this route. And then which table are we inserting into? It's going to be the matches table. So make sure to import it from schema and then choose which values you want to insert. The values are going to be an object where we're going to basically pass everything. And I'm noticing that this database is not imported. So let's import it coming from db.js. And we can pass everything by spreading parsed.data. This will include things such as the sport, the home team, away team, and so on. But we also want to pass some other data pieces in a bit of a different way to make sure they align with the validation that we have specified. So here we'll have to pass the start time separately because we have to wrap it in a new date. So I'll say new date parsed.data.start time. And just so we don't have to be super verbose like we are here, we can destructure those values from parsed. So I'll say destructured data and then destructure start time coming from parsed. That way, you can just say new date from the start time. You'll notice that it'll complain a bit right here, saying that the argument types do not match parameters, but we actually know that the start time that we pass into this function matches the schema, and the start time is an ISO date string. So it is a date, which means that it's going to work. So we can just continue. We'll do the same thing with the end time. So you can do that here and make sure to destructure it at the top. We'll also destructure the home score as well as the away score, just so that we can set the home score to be either home score, or if it doesn't exist, we can default it to 0 at the start. And we'll do the same thing with the away score. And finally, we gotta figure out the status. So the status will be set to get match status. This is that utility function that we created that takes a look at the start and end time and the current time and figures out what is the status. So to it, we just have to pass the start time and the end time, and that's it. Finally, you can say dot returning to make sure that we actually get back the new event that we created. This will specifically return the specified fields of the inserted rows. Finally, we can just return it to the front end by saying res.status, give it a status of 201, which means created, and send back the JSON that has the data key set to the event value. And with that, we are ready to test it out to see whether we can actually insert new matches into our database. To test it out, you can use any kind of an HTTP client. I like using HTTPy. You simply download it, and then it's super simple to use. It looks something like this. You can see that I still have the endpoint from my last video right here. It's the one coming from the full stack engineering course, specifically on Pern. So if you haven't checked it out yet, definitely give it a shot. With that in mind, I'll delete this endpoint and create a new one. Specifically, we want to make a post request to localhost 8000/matches. And just to make sure that our API is running, you can run it within your terminal and then send a GET request to matches. And you can see the dummy endpoint that simply says matches list. Now, if you head over to post and try to call it without any parameters, you'll see that's not going to cut it. So instead, you have to pass in the body, which can be in form of a text, and you have to write something like this. You need to pass the sport, which you can set to football, for example. You can add your favorite home teams and away teams, like JSM United, and you can pass the start and end time. You can get the current ISO string by just Googling it or running JavaScript for that and getting something like this, or feel free to pause the video and type it out by hand. Once you add the body and click send, you'll see that we'll get back 201 created with the data that now includes an ID of this newly created match within our database. That's always a good sign because besides the body data that we provided, it also got the ID, which means that it's actually in the database alongside the created at field. We can also add another, maybe cricket with India versus England, just so we have two. Now to verify, we've actually added some new rows into our database. You can go to your Neon project under tables, matches, and you can see that there are 2 matches right here. Perfect. But we also want to be able to retrieve this data within our application. So within this same file where we have the matchrouter.post, we'll edit this matchrouter.get to give us back the current data. As before, we'll parse it by saying parsed is equal to list matches query schema dot safe parse, and to it we want to pass the rec.query. Then if it's not parsed dot success, same as before, well, we can return the same error message, this one right here, that says res status 400, not invalid payload, but rather invalid query. And under details, we'll pass the more details about the error. But if everything is good, we want to be able to create a limit of how many matches we want to get back in a single call. Oh, let's make sure to properly close our function right here and not before. There we go. The limit will be set to math.min from parsed data .data.limit, if it already exists, if we're passing it through the front end, or 50. But it must not be larger than max limit. And we can define this max limit at the top by saying max limit is going to be set to like 100 matches. Then we can open up a new try and catch block. In the catch, we'll simply return an error of 500 with the JSON error that says failed to list matches. And in the try, we can simply return the data. So make this call asynchronous, and then you can say const data is equal to await db dot select. We want to select from the matches table. We want to order it by, this is going to be in descending order, so DESC, which you have to import from Drizzle ORM, specifically in descending order based on the matches.created@at field, so the newer ones will appear at the top. And then finally, you want to limit it by saying .limit with the limit that we have defined above. Once you get back the data, you can simply return it to the front end by saying res.json and then pass in the data. In this case, I'm putting it within an object. And that's it. Let's go ahead and make a request to this route within HTTP to see whether we get back the data. If I click send and clean up the body, you'll notice that parse data is not defined. That's because here I used parse data, but instead it should have been just parsed. So if you fix that and make another request, you'll see that we get back the data array that includes 2 new matches, with the one that we created last at the top. This is exactly what we expected. So back within our application, let's go ahead and create a new branch. You can do that by running git checkout -b, and you can call it feat/matches-endpoints. Then run git add dot, git commit -m, implement matches, post, and get routes, and run git push. Of course, you'll again have to set up the upstream to the remote repo. Once that is done, head back over to your GitHub repo and open up a new pull request for this new branch that we just created. This one is just a tiny bit longer than the previous one with 168 new lines, and you can see that CodeRabbit is already starting to assess it. It is easier to change the specification to fit the program than vice versa. Yeah, that's a good one if you don't really feel like coding something out. With that in mind, let's give it some time until it processes it, and hopefully it comes back with some good feedback. And there we go, the review's in. Quickly going through the walkthrough, we can see exactly what we've done. Introduced a complete matches feature for managing sports matches, including express routes for listing and creating matches with Zod validation schemas. And this is the sequence diagram that I've been telling you about. If you expand it, you'll be able to see exactly how our application works under the hood. The client will make a GET request to /matches with an optional limit number. That's going to be intercepted by the match router, which is going to move it over to Zod that is then going to validate the query against the list matches query schema. Only if it's valid, it'll make a call back to our database that'll get all the matches ordered by the created at date in a descending order with a limit of 50, give them back, and return a 200 with all the matches. The post works in a similar way. The client will make a request to post /matches with the correct data, will validate it, get the match status, and if everything is good, insert it into the database and get back the 201 created. Being able to visualize the code we just wrote is super useful. Coding is all about letters, but being able to see some lines from time to time really changes perspective and helps you visualize things better. Now, let's see whether CodeRabbit has something to say about our code. There is one nitpick comments saying that dateparse accepts non-ISO formats, risking inconsistent parsing across environments. Instead, Zod4 provides ZISO datetime for strict validation, and it even gave us a suggested refactor, which is actually much shorter and more convenient. So we can just copy this part, head back over into our validation file, and where we have the ISO date string, we can now just replace it with ZISO datetime. As a matter of fact, it is super short right now that we don't even have to turn it into a new variable. We can just use it right here and here. Damn, this was a pretty nice fix. And Zod4 is pretty new, so the fact that CodeRabbit was able to pick the latest docs from Zod4 is amazing. I'm pretty sure this wasn't possible in Zod3, and this was just the nitpick comments. But the next one is referring to our matches GET request, I think. Return Zod error issues directly instead of stringifying the error. JSON stringify produces an object because Zod properties are non-enumerable. Use parsed error issues to return structured error diagnostics to client and align with Zod's error API. Okay, another great catch. So the only thing we have to change is instead of stringifying the error, we actually provide the part that matters, and that is parse.errors.issues. So back within our routes matches, I think this is in the post request. You can see that we are stringifying the error right here, but instead we need to say parsed.error.issues. And I think we had a similar thing in the get route. Yep, here we're stringifying it as well, but instead what we can do is say parsed.error.issues. So it's in both get and post. Then we have another major issue where we have to fix destructuring before validation success check. Because parse data is undefined if the validation fails, so the destructure will throw an error before the 400 response. We have to move the destructure after the parse success guard. This is actually a big one and could literally result in getting our server turned off if it goes wrong. So there's a proposed fix right here. We simply have to move this line after the parsed guard. I'll go back right here, and here we are doing the destructuring in the post request. So I have to move this here. We can only destructure this once we know that there is something to be destructured. See, these little things are exactly what I was telling you about that CodeRabbit will fix seamlessly. Then we have another minor one saying avoid leaking internal error details in 500 responses. This also has something to do with this JSON stringify. So instead, it's suggesting to omit those entirely. But I think we already fixed it with the previous suggestion it gave by only returning the issues right here. So that means that we can push all the latest changes by running git add dot git commit -m implement CodeRabbit suggested fixes, and then run git push. If you do that, the changes will automatically be recognized, and you can merge this pull request safely, knowing that we don't have any bugs. Courtesy of CodeRabbit. Now, when you do that, you can clear a terminal, switch back over to the main branch by running git checkout main, and pull all the latest changes. Perfect. You now have a clean foundation, a real database schema, REST endpoints to create and list matches. All of it fully validated, production style. So now the backend can create match data. But the user still has one problem. They only see updates when they refresh. That's not real time. So in the next lesson, we're going to fix this by adding a WebSocket server. So the exact moment the match is created, every connected client gets the update instantly. No refresh like what I'm doing right now, no polling, just live. So let's build the WebSocket layer. In this lesson, you're going to implement a WebSocket server to transition your app from a traditional request-response model to a persistent bidirectional architecture. A persistent bidirectional architecture is a connection that stays open indefinitely between the user and the server. In a standard setup, the connection closes as soon as the data is sent, but here, the pipe remains active so both sides can send messages at any time, as you learned in the crash course. You'll learn how to hook this server into your existing setup and push match events to every connected fan the moment they happen. It all begins with installing the WebSocket library. As I mentioned before, we'll use the native WS library, which is fast and thoroughly tested WebSocket implementation for Node.js. So just run npm install WS. As soon as you install it, which will happen literally in seconds, you can immediately create a new file, which will manage all connected clients and provide the broadcasting logic. That's going to happen within source, and then here you can create another folder, call it WS, and within it create a new file called server.js. And let's dive into creating it. First, let's create a function that'll send a JSON object to a specific client. Essentially, it's going to be a helper function that'll prevent repetitive JSON.stringify calls and ensure the socket is actually open before sending. So I'll say function send JSON, and it'll accept the socket and payload as params. As I said, we'll check whether the socket is active by verifying that its ready state is equal to WebSocket.open. Make sure to import this WebSocket by saying import WebSocket coming from WS. If it is not open, we can simply exit. So I'll say return. This is called a guard function. But if it is open, we'll say socket.send, and we will stringify the payload that we want to send over to the client. A simple helper function. After that, we'll create another function called broadcast, and it does what the name suggests. It'll send data to every connected user. So we simply need to get in the WSS, which is going to be the WebSocket server, and the payload. And within here, we'll iterate through all the clients within our WebSocket server by saying for const client of WSS clients. This set right here contains all the active connections. And within it, we're going to do the same thing we've done before, which is first check whether the state is not open. And if that is the case, return. But in this case, we're not checking the state of the socket, but rather the client. And if the client is ready, then we can actually send the message. Perfect. So now we have two helper functions. And finally, we want to attach the WebSocket logic to our Node server. We can do that by saying export function attach WebSocket server, which takes in the server as the parameter. And we'll create a new WebSocket server by saying new WebSocket server, which you have to import from WS at the top. First, you can pass the server itself. This function will receive the HTTP server instance created by Express, and we're passing it into the WebSocket so that it can attach itself to the same underlying server. The HTTP server will then listen on that port and handle normal REST requests, while the WebSocket uses the same server to listen for upgrade requests. This avoids running a separate port just for WebSockets. Using the same server simplifies deployment and networking. The second thing you want to provide is the path. This is a string representing the WebSocket endpoint, and only requests made to this exact path are eligible for WebSocket upgrades. Requests to other paths continue to be handled by Express normally. So in this case, we'll set the path to a simple /WS. This keeps WebSocket traffic clearly separated from the REST API routes. In this codebase, WS is reserved for all the live match updates. And then finally, we can also pass the max payload. This is a number represented in bytes, and it defines the maximum size allowed for a single incoming WebSocket message. We can do something like 124 times 124, which equals 1 megabyte. If a client sends a message that is larger than this, it is automatically requested. This acts as a security measure against memory abuse or flooding. And since it doesn't take a lot of space, we can actually just display all of this in a single line. Then, once we actually have the WebSocket server, let's do something with it. I'll say WSS on connection. We get access to this socket, and we want to send an initial message to confirm the link is active. So now we can use this send JSON helper function. We're sending it to the socket with the following payload that's going to include a type of welcome. Then we also want to handle the errors to prevent the server from crashing on bad disconnects. So I'll say socket.on error. We'll simply pass the console.error right here. Finally, below the on connection, we want to return a clean function that the rest of the app can use. So that's going to be function broadcast match created. It'll take in the match and it'll simply broadcast it by using our broadcast utility function we created to the entire WebSocket server. The type will be match underscore created, and the data will be the match that we're talking about. Finally, we can return this broadcast match created function from the attach WebSocket server so that when we attach it, everybody can use this function. For now, that is it. We created two helper functions. We created a new WebSocket server. We gave it an on connection, on error, and the ability to broadcast match created events to the entire application. Now head over to source index.js, which is our main server, and let's hook it up with the WebSocket server. Keep in mind that Express is a framework built on top of Node.js HTTP module. To use WebSockets, we need to explicitly create the HTTP server so that the WS library can hook into it. So let's do that. I'll rename this port to use capital letters to denote that it is a constant. And instead of keeping track of it here, we'll actually move it over to our envs. So head back over to your .env and add a port environment variable that's going to be set to 8000. While we're here, we can also add a host of 0000. Perfect. And it doesn't have to be a string because everything right here is a string by default. So right here for the port, we can convert it into a number, process.env.port, or it can be 8000 by default. And we can do a similar thing for the host. So right here, we can say host, and the host will be set to process.env.host, or it's going to be that string that we defined just before. After that, and after we define our Express application, we want to wrap the Express app in a standard Node HTTP server, allowing both HTTP routes and WebSocket upgrades to coexist on one port. You can do that by saying const server is equal to http.createServer and simply pass in the Express app into it. This HTTP is imported right here from the top by saying import HTTP from HTTP. And it looks like coding assistant for Node.js is disabled. So let's simply automatically go ahead and enable it for WebStorm, which is going to install types and make it work right off the bat so that now we know exactly what this create server does alongside with this example. After that, right below our router right here, we can say const and destructure the broadcast match created coming from attach WebSocket server, and then we pass in the server we created. Here, we're basically initializing a WebSocket and getting access to the broadcast function. The reason we're getting access to it is so we can store it to app.locals.broadcast match created, like this. App locals is Express's global object accessible from any request. And finally, instead of app listen, we'll say server.listen on a specific port through a specific host. And then we can form the base URL a bit more professionally by saying base URL is equal to, if host is triple equal to 000, in that case, we are on localhost. So I'll say HTTP localhost, but let's make this a template string. And this localhost, of course, ends with the port that we're on. Else, if we're not on localhost, then we might be on HTTP, where we're defining both the host and the port. So I'll say HTTP / host, and then port, like this. Finally, we can console log server running on, and now we can put the base URL here. And we can also say console log WebSocket Server is running on base URL, but we'll use the dot replace on it, and we'll replace HTTP with WS for WebSocket, and then we're going to append /WS on it. Remember, this is a special endpoint telling our app that we need to treat it through the WebSocket server. Next, we have to trigger the broadcast whenever a match is created via the REST API. You know where that happens. That's right here within our routes, matches, and specifically, we're talking about the post route. So just after we insert it into the database, you want to check if res.app.locals.broadcast match created. If that exists, then we want to push the new match data to all the connected fans immediately by saying res.app.locals.broadcast match created. We're calling it and passing in this new event we just created. Pretty cool, right? And it should just work right off the bat. To test it out, you can install WSCat if you didn't install it in the crash course part by running sudo npm -g wscat, or if you're in Windows, you might not even need sudo. You'll need to insert your password and get it right. Then WSCat will be installed globally. Make sure that your server is running. You can see now that the message says server running on HTTP localhost 8000. Oh, but I think here we missed the colon. So that's going to be localhost and then the port. So if we fix this, now it is 8000, and the WebSocket server running on WS, localhost 8000 WS. So now we want to split this terminal, and then we want to open up the WS client on the same port in a new window. That's going to look like this: WSCat-C. The -C flag stands for connect, WS : localhost 8000 /WS. And press enter. When you run this, your terminal stays locked in an open connection. The moment your server calls send JSON socket type welcome, the data will immediately appear in your terminal, and it'll sit and wait silently until the server pushes more data. So now what I want to do is keep my HTTP or any REST client open on the left side while we're keeping track of the changes happening right here on the connected devices, or to the fans watching. We have to switch it over to a post request to localhost 8000 /matches, and we want to pass in some body. We can do the same thing that we did before. Make sure the sport is there, home team, away team, start time, and end time. And as soon as you press send, you should be able to see a new event on the client instantly. 3, 2, 1. There we go. A new match just got created. This happens because your express route finished the database work and then called app locals broadcast match created event, which pushed the data through the pipe to the WS client. You're smart. You understand that this data right here doesn't belong just within the terminal. But if we can get it here, that means that any client front-end application can get it too. And you can do a lot of stuff with JSON. You can read this data of match created and display some kind of a card. That card can have an icon of a football. It can also have different logos for different teams, and it can stream in scores in real time. That's what we've been waiting for this entire course. And we just proved that it works. Now we can stop the second terminal from running, and we can push the changes by checking out to a new branch, git checkout -b feat WebSocket Server, maybe the most important one in this course. Then run git add dot git commit -m implement the WebSocket Server, and then finally git push. Of course, we have to set the upstream and wait for CodeRabbit to do its thing. And there we go. If you take a look at the walkthrough, this is going to be a big one. This PR introduces WebSocket server support to an Express application by integrating the WS library, creating an HTTP server wrapper, and implementing a broadcast mechanism for match creation events shared with connected clients. Exactly what we've done. And here's a little sequence diagram where a user makes a post request to /matches. This is exactly what we've done using HTTP. Then we talk to our HTTP server, which then talks to the match router, which creates a match in storage. But then we also talk to our WebSocket server, which broadcasts the match created event immediately to all the connected clients, which means that they are receiving real-time upgrades. Pretty cool, right? So let's see what CodeRabbit has to say about this PR. We even get a little poem. Real-time matches broadcast through the night. From match creation to clients far and wide, events dance across the network tide. Pretty cool. And let's see what it has to say about our code. There are 4 nitpick comments. These are very simple. Yep, one of the suggestions is about implementing the ping pong heartbeat to detect and clean up dead connections. And what I love about it is that it even provides us with the code that we can add to make it work. To be honest, I'm very surprised that it gave me the exact type of feedback and improvement that even I wanted to teach you how to do a bit later in the course. But it's possible that I would have forgotten, or that something else would get in the way. Like this, we can immediately add it to our code and learn how it works. So let's go ahead and copy this block of code. Then head over to our server and want to override the attach WebSocket server function. Of course, you want to remove all the pluses. You can do that by holding the Alt key and selecting right here before them. And then you can just press backspace once to fix all the indentation. Great. So now let's actually go through it to understand how it's working. First, on connection, we are attaching the isAlive variable to the socket and setting it to true. Then on Pong, we are still making sure that it is true. But then we set up a very simple JavaScript interval. We then iterate through all of the clients. We check if isAlive is set to false. In that case, we terminate them. But if it's not false already, we set it to false and then ping it. Then if it doesn't reply in this amount of time, it'll automatically die. We also want to clear this interval. And that's it. Now, even though this was a nitpick comment, it was an amazing one. Consider alternative patterns for sharing the broadcast function. Okay, this is interesting. Using app locals works, but tightly couples routes to this specific implementation detail. For larger applications, consider dependency injection or even an event emitter pattern for better testability and decoupling. And this is the perfect example for when I was telling you that CodeRabbit can be a teacher too, because it can point to some things that you didn't even know existed. Some complex patterns such as dependency injection or event emitter patterns that are going to make your code better. So now you could spend an additional half an hour or an hour trying to implement this, and you will have learned a lot. This one is simple. Consider wrapping the broadcast in a try-catch block to prevent silent failures. Let's take a look at the one that is critical in this case. Return should actually be continue in a broadcast loop, because using return on line 11 will exit the entire function when encountering the first non-open client, preventing the message from being broadcasted to remaining clients. This should be continue instead to skip only that client. Did I really make that big of a mistake? I mean, it looks like I did. So here, we just need to set it to continue. Back within server, right here when we're looping through it in broadcast, I'll just replace this return with a continue. I mean, even though it was a small commit with what, like 80 lines of code, CodeRabbit was able to find a critical mistake that I did. So let's go ahead and push those changes by running git add dot git commit -m implement CodeRabbit suggested fixes and git push. As soon as the changes are pushed, you can just go ahead and merge the pull request. Once it is merged, you can check out back to the main branch and run git pull to pull the latest changes. That's it. You actually created a WebSocket server and hooked it up to a REST API. Congrats. That's what you came to this course for, right? But we're going to take it even further in the upcoming lessons. So let's go. You've officially crossed the bridge into real-time web development. By attaching a WebSocket server to your HTTP server, you've enabled your application to push data instantly without waiting for a user to refresh. But at the same time, opening live pipes like WebSockets makes your server vulnerable to new kinds of abuse. Because these connections stay open, a malicious user could try to overwhelm your system with thousands of connections or spam your endpoints to crash the service. So in this lesson, you're going to learn how to protect your real-time apps using Arcjet. You'll implement security layers like rate limiting and bot protection to ensure your live stream remains fast and available for real fans. Actually, we'll add security measures for both HTTP server and the WebSocket server so that everything's safe from the get-go. And this is super important because we're building a sports app, and sports apps can be targets for scraping bots to get the data or connection bursts during high-profile matches. So click the special Arcjet link down in the description and create a new account completely for free. You can see that I already used Arcjet to track some of my other projects. So go ahead and create a new site. Let's call it something like sports. Click create and copy the Arcjet key. Then head over to your .env and let's add a comment for Arcjet where you can add the Arcjet key and make it equal to this key you just copied. We can also add the Arcjet environment at the start set to development, which will have to switch over to production in a production environment later on when we deploy our application. Now, we want to install the core Arcjet SDK and the inspection tool for debugging security decisions. That's npm install @arcjet/node and @arcjet/inspect. Arcjet is lightweight, so it's going to install pretty quickly. And once it does, we can create a new file in the root of our application within the source folder called arcjet.js. This file will centralize our security logic. For better production-level applications, this should even be put in a separate config folder. But since we're starting small, we can put it here for now. You can move it anytime, it'll work the same. In this file, we have to define a set of rules separately for HTTP, like higher limits, and WebSocket, stricter limits to prevent handshake spam. Why? Because the behavior of a user browsing an API through HTTP is very different from a user opening a persistent connection like they do using WebSockets. So first things first, let's get access to our environment variables within variables in this file. So you can say arcjet key is equal to process.env.arcjet-key. And we can do the same thing with arcjet mode, which is going to be process.env.arcjet_mode. And if that is set to dry_run, then we'll set it to dry run, else we'll set it to live. The dry run mode allows you to see what Arcjet would block without actually blocking it. Now we'll do a quick check if there is no Arcjet key, in that case, we can throw a new error saying something along the lines of arcjet underscore key environment variable is missing. And then we are ready to create a new instance of Arcjet. Let's make sure to spell this properly first. Arcjet. So we're going to export a new instance of HTTP Arcjet, which is going to be equal to if Arcjet key exists. In that case, we can make it equal to an instance of Arcjet, which you have to import from Arcjet node. And then to it, we can provide some additional options. Else, if we don't have a key, we can simply set it to null, because then we can't create a new instance of Arcjet. And we'll do exactly the same thing for the second instance of Arcjet that's going to protect our WebSocket. So I'll call this WS Arcjet, and we're doing the same thing. So which settings or options do we have to pass to it? First one is the key set to the Arcjet key, and then we pass the rules. Rules is going to be an array, and specifically we're going to pass two separate rules. Shield, which will have a mode set to Arcjet mode, and this shield has to be imported from Arcjet node. This protects us against most common attacks like SQL injections or XSS by analyzing the structure of the incoming requests without us having to do anything else besides write the code for this line. And we'll also do a detect bot rule, which you also have to import from Arcjet, that'll accept two options: mode set to Arcjet mode, as well as allow. There are some specific bots that we do want to allow. Some scraping bots are not good, but scraping bots for search engines, for example, to make sure that our sports application ranks high on Google or other search engines, well, those bots are welcome. So I'll say allow category search engine, as well as category set to preview. This is for when you send links so that you can display that nice thumbnail in whichever social messaging app you're using so that they don't even have to click the link, but you can show a nice image. Now, below detect bot, we're going to add the next rule, which is going to be the rule for rate limiting. Specifically, we're going to use a sliding window rate limiting algorithm. It's a sophisticated counter that tracks requests over a moving time frame. Like, we can set it to 10 seconds. So I'll set the mode to be set to Arcjet mode, the interval to be set to 10 seconds, and finally a max set to 50. This means that we're allowing a max of 50 requests every 10 seconds per an IP address. And now I will copy these rules and move them over into our WebSocket Arcjet instance as well, but we're going to change them a bit. Specifically, we're going to change the sliding window. We want to narrow the window down to stop the connection spam. So I'll set it only to 2 seconds, and I'll allow a max of 5 requests in an interval of 2 seconds. What this means is only 5 connection attempts every 2 seconds. I'll collapse both of these. And now we want to protect the standard REST routes by exporting and creating a new function called security middleware. This function will return another async function, so it's a wrapper function that accepts a request, a response, and the next parameter. Whenever you're building middleware, it needs to have a next, so that if we decide to pass it through to our API, we can just do that using next, and then the next endpoint gets called. So let's use the powers of Arcjet here. I'll say if there is no HTTP Arcjet, then we can simply return next, because the instance of Arcjet that was supposed to protect our HTTP isn't there. That shouldn't happen though. So let's open up a try and catch block. In the catch, we can simply console.error the actual error. We can say something like Arcjet middleware error and then log it. And we'll also return a res.status of 503.json error set to service unavailable, like this. And now let's focus on what happens if everything goes right. Here, Arcjet will have to make a decision. So say const decision is equal to await HTTP Arcjet dot protect. This protect method will analyze the request locally where possible and otherwise call the Arcjet decision API to be able to figure out whether we let this request through or we stop it in its tracks. And it'll do that based on the rules that we gave it right here. So it's fully customizable. Then we have to write the code that'll decide what happens if the decision is to block it or if it's to let it through. If the decision dot is denied, in that case, we can open up a block and check for the reason why it's denied. If decision dot reason dot is rate limit, in that case, we can return a res.status of 429, which typically means rate limited, and a JSON message with an error of too many requests. If that's not the reason, it must be some other reason, so we're going to simply give it a return res.status of 403, and it'll simply say forbidden. But if everything is right, we can go below this try and catch block and simply call the next function. This means that the decision is set to allow, which means that we'll move to the next step. Now head over to our HTTP server, and right here above app.use matches, we want to activate this new middleware by saying app.use, and we want to call security middleware like this. Make sure to actually call it and import it from arcjet.js. Now, a WebSocket connection starts with an HTTP GET request, that handshake you learned about before, that's asking to upgrade to become a socket. We'll need to intercept and secure it so users won't be able to create too many connections. To do that, head over to your WS server.js, and right here, when we try to attach the WebSocket to our HTTP client, on connection, we want to add an if statement and check whether WS Arcjet exists. You'll need to import it from Arcjet. If it does, we can open up a try and catch block. In the catch, we'll simply console.error, something like WS connection error, and also close the socket because something went wrong. So socket.close, we need to pass in the code that we'll get soon, as well as the reason. And then we can simply return. In the try, we'll do the same thing as before. So say const decision is equal to await. This means that we have to make this function asynchronous, and we'll also get access to the request that we're trying to access. So let's call the WS Arcjet dot protect to protect our request. Then, as before, we have to figure out whether the decision has been denied. So if decision is denied, in that case, we can figure out why. So const code is equal to decision dot reason dot is rate limit. If it's rate limit, we'll set the code to 1013. This means try again later, rate limited. Else, we'll set it to 1008, which is a policy violation, like a bot detected. Then, based on that, we can also do the reason. So const reason is equal to if decision dot reason dot is rate limit. If it is, we'll then give a message, something like rate limit exceeded. Else, we'll say something like access denied. And we'll close the socket by saying socket.close, pass in the code and the reason, and finally return. So here in the catch, we don't have to pass the code and the reason because we don't have it, but we can say that it'll be 1011, which is a general error, and we'll say server security error. All set. That's it. You only needed to add this block of code, and Arcjet will protect your WebSocket server. And don't forget that just by adding this part, this middleware right here to our server, it's protecting all the endpoints of our REST API as well. Okay, so we're all set, and it's time to test these servers. But this time, we'll do it on a bigger level. For this, I actually had to wake up a hacker in myself to try to get Arcjet to block us. So I prepared a line of code that will run. I'll provide it to you in the video kit link down in the description. You'll need to copy it and then paste it right here. It'll look something like this. For I in 1 out of 60, do curl, HTTP code, and try to speak to our local host. This will try to make requests to both servers rapidly in very little time. This is how we can verify that Arcjet will perform well in actual high traffic scenarios. So first, we test the HTTP server through a burst, or also known as a spam test. Press enter, and you should be able to see all the requests, and make sure that our server is actually running. Right now, it looks like the Arcjet key environment variable is missing. Thankfully, we added this message that's going to alert us. So let's see, why is it not picking it up? Arcjet underscore key is right here. And then if I head over to Arcjet, it's looking at Arcjet key. Oh, I had a typo right here. That's why it wasn't working. So now that our server is actually running, you can see that right here. In my other terminal, I will rerun the same command. But even though I was expecting to see some 200s until we hit a rate limit, we got all 403s. If you tried one more time, again 403. That's most likely because Arcjet is detecting these as bots. So if you head over to your dashboard under sports, you'll be able to see that we got blocked, and we got blocked well. And that's because it recognized that we're trying to call it not in a normal way through a REST API client or something. We were calling it through a curl command. That's why we got blocked. So this is great. This means that bot detection is working. But if I comment that out and let bots through, I want to see whether it'll rate limit us. So now with that rule commented out, I'll call it one more time. Take a look. We're getting 200s. We should be getting, I think, about 40 200s. And then the last one should be 429 because we got rate limited. Same thing again. It's only a 10-second limit, so you'll be able to see it right here. This time it went all through. So if you go back, you'll be able to see that some went through, but there is one that hit a rate limit, specifically a limit of max 50. This means that both the bot detection and rate limiting work. So far, we've been testing the HTTP Arcjet protection, but now let's also test the WebSocket. For this one, I'll also provide you with a little hacky block of code that I wrote to test this out. And instead of running it in the terminal, we'll run it within our browser. So open up your console and paste what you just copied from the video kit link down in the description. We're again doing a loop 10 times, and we're creating new clients. And again, make sure this WebSocket is the same as what you have in your code. If you run this, you'll see that a couple of sockets will be opened successfully, which is what we expected. But then once we start noticing that so many connections are trying to be opened, it's highly likely that something is going wrong. So we are going to close them because we exceeded the rate limit. This means that you just successfully secured your application by wrapping both your REST API and your WebSocket handshakes in a professional security shield. By testing your server with burst requests, you've seen how Arcjet automatically steps in to block spam and protect your resources. So you can now rest easy knowing that your live stream is defended against so many malicious bots or users and accidental overloads. And you can take it even further and implement other Arcjet features, but even with what we have now, you're more than good to go. So let's create a new branch by running git checkout -b and call it feat Arcjet. Then run git add dot, git commit -m, implement Arcjet security, and git push. Of course, you'll have to set upstream. Once that's done, you'll be able to open up a new pull request. And let's wait until it's processed by the Rabbit. Very soon, we get a walkthrough that says that we're integrating Arcjet security middleware to protect both the HTTP and WebSocket endpoints. Perfect. And there's even a sequence diagram that tells us exactly how that protection is working. This time, we also have one potential critical issue, and that is to move the protect call to the upgrade event handler before the WebSocket handshake. Okay, this is interesting. Let me read a bit more about it. The close code mapping, 1013 for rate limit and 1008 for access denied, 1011 for server error is correct. But Arcjet's documented pattern is to call protect on the raw HTTP upgrade request in the server.on upgrade handler, not in the connection event. This allows rejecting the upgrade before the WebSocket handshake completes, which is more efficient and follows Arcjet's recommended best practices of calling protect once per request before any connection processing. I mean, this is just amazing. This is not the first time that CodeRabbit was able to directly fetch the documentation from another library and fetch their latest version and tell me how to fix it. In this case, it even provided a reference pattern directly from the Arcjet docs, where it says that we should be calling the server.on upgrade instead. And then it provided a prompt for AI agents to solve this issue for us. This is absolutely amazing. So let me copy this prompt, head back over to Junie, and type it out right here. In source WS server, around lines 21 to 37, move the Arcjet protect callout of the WS on connection handler into the HTTP server's upgrade event handler. Perfect. Let's see how well it does it. This is going to be happening right here. Within this part, it'll try to understand what's happening and edit it. Specifically, this change is happening within server.js, and you can see that it did exactly what we asked. It even created some test script that we can run to see whether it works or not. This is pretty cool. And it was a bit more specific when explaining what exactly went wrong. Perfect. Let's go ahead and push this by saying git add dot, git commit -m, implement CodeRabbit suggested fixes, and run git push. As soon as you do this, you'll be able to merge the pull request. Then, back within the code, run git checkout back to the main branch, pull the latest changes, and we are ready to continue with the application. In this lesson, you're going to implement the REST API routes for your commentary system, which is the main data point of your live sports coverage. While the match API handles the overall structure, the commentary API captures the story of the game, the goals, fouls, and big moments that keep fans engaged. You'll also level up your development workflow by using AI prompt engineering for generating boilerplate code. So instead of writing repetitive code manually, you'll learn how to make AI handle the heavy lifting, allowing you to focus on the application's logic and architecture. So let's dive right in. You can open up Junie or your AI coding agent of choice, and let's write our first prompt. We'll start with the usual, act as a senior Node.js developer using Zod, create a validation file that's going to be under source validation commentary.js. And the goal here is to, number one, create a list commentary query schema, an object with an optional limit, which is going to be coerced into a number, positive with a max of 100. Then we also need to create a create commentary schema, which needs to include fields for minutes. This is going to be a non-negative integer, a sequence, a period, which is going to be a string, an event type, and all of this is coming from the diagram that I showed you before. The actor who is doing the event, the team, and the message, which is going to be a required string. And then metadata, which is going to be a record of additional JSON data. And finally, tags, which is going to be an array of strings. In this case, we wanted to use ES modules and export the schemas so that we can use them later on. Perfect. So let's see how well it does it. It'll do it in the file we told it to do, but first it has to create that file, so it'll ask me to use the terminal. So under validation, it'll update the task and immediately add it. You can see that it did exactly what we asked. It created a list commentary schema with a limit, as well as the create commentary schema. Next, we need a post route to add commentary to a specific port. Same as you did with the post match route where we created a match. So now we won't practice manually typing the characters again, but rather we'll practice creating this with AI. It's a perfect opportunity to improve your prompt engineering skills. So create a new file under routes and call it commentary.js and simply export the router from it. So that's going to be export const commentary router is equal to router coming from express. Make sure to call it. And then we can create a base route, commentary router dot get /recres, and we'll return a res.status of 200. And within it, we'll return a JSON, so .json, that's going to contain a message, which later on will return a commentary list, just like what we have done with the matches. Now we can go to our source index.js, that is right here, and similarly how we imported the match router and used it right here, we'll do the same thing with the commentaries. The URL is going to be matches :ID, so it's going to be within a specific match, and then each one of these matches will have a commentary, which is going to be handled by the commentary router, which you need to import. Now, once again, we can open up Juni, and this time we'll tell it, again, act as a senior Node.js developer and generate a post route for commentary.js file using drizzle ORM. Number one is to validate rec.params using the match ID param schema and request.body using create commentary schema, and then insert the data into the commentary table and return the result. Once again, we want to use ES modules and handle errors with try and catch. Again, I am being very descriptive right here, and that is to ensure that both of us get the same results. If I was doing this on my own, I would type it much more quickly with fewer instructions. So now it's going to create it. If you head over to commentary, we asked it to create a post routes for creating new commentaries that's going to be validated with Zod and through Drizzle. So let's see how quickly it can do it. There we go. It took some time to update the task progress, and immediately after, it added a 31 new line for the commentary post request. You can see right here that it's first getting the param results by parsing the params we're passing into it. It's handling the non-successful event if it's invalid, and then it's getting the access to everything from the body that we're passing to this create request. If body doesn't exist, then again, it sends an error, which is good. But then if it does, it destructures the data, takes the rest, and inserts a new commentary into the commentary table and returns it back to the front end. This is exactly what we expected. Now, make sure your application is running, and then head back over to HTTP. Now we can make a GET request to /matches to be able to get a list of matches that we've created so far, and then take an ID of a single match, for example, this last one with an ID of 3, and use that ID to create a post request for creating a commentary that's going to attach this additional data to the match. So that's going to be /3/commentary. And then we'll do a post request. This time for the data, we won't pass the data just for the match itself, but rather something like this, which is just a small event happening within this large match. It happens at a minute 42. It's 120th in the sequence, for example. The period is second half with an event type of goal, which was scored by Alex Morgan for FC Neon. And we have the message. Goal! Powerful finish from the edge of the box. Amazing. We can also provide some additional metadata, such as assists or tags. So let's go ahead and send it. And you'll see that we get a 500 cannot read properties of undefined reading Zod. So we know the issue is something regarding Zod and how we're parsing the data. So let's head over to our commentary validation and see here that we have an issue with metadata z.record. What we can do instead of z.any, we can also add z.string at the start. So we tell it that it can be a string too. And then notice how here we're using minutes. But then back in our application, I said minute. So instead, what we can do is also say minutes. That way we're staying consistent. Now let me retry it and also make sure that it says minutes right here. Or if you want to stick with minute, that's also totally okay, but then you have to change it in the code as well. For now, I'll go with minutes and click send. And you'll get a 201 created. Now, for this sports app that we're building, we want to get the live feed effect, which means that we want to get the newest event at the top. So we need to create a GET request that'll get the list of all commentaries for that match sorted by time with some kind of a limit. You can totally write it on your own, or we can use a quick prompt to generate it. Since we've done it for the matches, I'll go ahead and ask Junie to do it for me. You can pause this video and type it out by hand. Using Drizzle ORM and Express, generate a get/route for a nested commentary router. First, validate request params using matchID param schema and reqquery using list commentary query schema. Then fetch data from the commentary table where the matchID equals the ID from params, order the results by created at in descending order so newest events appear first, apply a limit based on query parameter defaulting to 100, and use ES6 modules with handling errors and try and catch blocks. There we go. The get route got implemented. Let's see how it did it. Once again, we're properly validating all the params, and we have proper error handling right here. Then we get the match ID and the limit. We set the limit, and then we get the results from the database. And then we return it. That's it. So back in HTTP, instead of making a post request to commentaries, which you can do, you can make a couple more requests just so we have more events in there. But now we're going to make a GET request to matches 2. To that, we haven't added any commentaries yet. So if you try to get it, you'll get empty data. But for the match number 3, since we inserted some events into it, you should be able to see a list of commentaries associated with that match. Just imagine how we can display this on the front end. Even though this is great, we're still in the request response world. You can create a goal in the database, but your users still have to hit refresh to see it. That is not acceptable in a real-world sports application. So in the next lesson, you're going to fuse this commentary system with your WebSocket server and start broadcasting every commentary update to all the connected fans instantly. In this lesson, we solve a massive scalability and user experience problem. In a high-traffic sports app, you might have thousands of users online. And if a goal happens in a football match, you don't want to interrupt the fans who are only watching tennis. So before this lesson, for match broadcasts, we broadcasted updates to everyone, every single user. But in this lesson, we'll implement a pub sub or publish subscribe system where commentary updates are only sent to fans who have joined that specific match. So with these types of subscriptions, you aren't sending data that the clients don't want to receive. That way, it improves client performance, experience, and helps with scalability. So let me teach you how you can implement this new pattern within all of your upcoming real-time applications. First, head over to source WS server. This is our WebSocket server where we have the send JSON and broadcast utility functions, as well as our big attach WebSocket server function. Right at the top, we want to create a new variable called match subscribers, which is going to be set to a new map. A map is very similar to an array. Here, we want to track which sockets are subscribed to which matches. And we're using a map because it automatically prevents a user from being added twice to the same match. That's the only difference between that and an array. Then we also have to add some additional helper functions. such as a function called subscribe that's going to receive a match ID and a socket. And then if no match subscribers dot has match ID within it, then we can actually subscribe it. So we'll say match subscribers dot set match ID, and we'll pass in the new set. We're creating this set only for the first person watching the match. And we can add this specific connection or the user to the matches listener list by saying match subscribers dot get match ID, and then we'll say dot add socket. Now we want to do a similar thing for unsubscribe. I'll do it right below by saying function unsubscribe that takes in the match ID and the socket. We first have to get all the subscribers by saying subscribers is equal to match subscribers dot get match ID. If there are no subscribers, in that case, we'll simply exit out of this function. But else, we'll check if subscribers dot size is equal to 0. In that case, we simply want to remove the connection from the list by saying match subscribers dot delete match ID. We're essentially deleting that key to save server memory. And finally, we'll create a third utility function. This is the most important part for stability. It'll be called cleanup subscriptions. That'll accept the socket, and we're gonna map over all of the subscriptions by saying const match ID of socket.subscriptions, and we want to unsubscribe the match ID from the socket. Essentially, what we're doing here is when a user closes their browser or loses the internet, we loop through the local subscription set and remove them from all match rooms. Oh, and right here in unsubscribe, I forgot to add subscribers dot delete socket. So we want to remove them from that socket. Right now, there's a yellow squiggly line under socket subscriptions. If it's still relevant, we'll get back to this later on. And finally, let's create the last utility function that's going to send data only to people interested in a specific match. I'll call it function broadcast to match. Of course, we need to know the match ID and the payload that we want to broadcast. We can first get access to all the subscribers by saying match subscribers.get for that specific match. If there are no subscribers, or if subscribers.size is equal to 0, we'll simply exit out of the function. Else, we'll get access to the message that we want to send to them by stringifying the payload, and then we'll map over all of the clients that are belonging to subscribers of this specific match, and then we'll check if client.readyState is equal to WebSocket open. Don't forget that, that's very important. If the ready state is equal to open, finally, we are ready to say client.send and send them the message. Then we have this previous broadcast function, which is basically broadcast to all. So we can just rename it to broadcast to all. And then we can rename it later on when it's being used. Broadcast match created, broadcast to all. Because now we have this other broadcast as well that is all about broadcasting to a specific match. So I'll put it a bit below right here. There we go. And we can collapse these functions and get ready to actually use them. The messages that we sent have to be handled. They're going to be coming in all sorts of different formats, so we make sure that we're handling them the right way. For that reason, I'll create a function called handle message that's going to accept the socket and the data. We can define a scoped variable called message and open up a try and catch block. In the catch, we'll simply send JSON to a socket with a type of error, and message is going to be set to invalid JSON, because if we can't properly parse it, then it's of no use. So in the try, we can try to parse it by setting the message variable to be equal to json.parse data.toString. Now, at this point, we already have the message. So let's check if message question mark dot type is equal to subscribe, and if number dot is integer of the specific message dot match ID, if that is the case, then we can actually try to subscribe the user. So right here, I'll say subscribe. We'll use this function that we created before, message.matchID, as well as socket. Then we'll also track it locally on the socket by saying socket.subscriptions.add message.matchID. And now remember why we got this warning right here, that this is unresolved variable subscriptions. It didn't know whether it's going to actually have some things on it, but you can see here that we're adding it. Finally, we can send the JSON message to a specific socket with a type not as error, but the type of subscribed with a match ID of message.matchID. And then right after it, we can exit the function. This is happening if the message is of a type subscribe. But now let's handle the other case. If the message is of a type, you can guess it, unsubscribe, and if the number is a valid integer. If that is the case, we will call unsubscribe helper function and pass in the message.matchID and the socket. We'll also delete it locally by saying socket.subscriptions.delete message.matchID to remove it from local track, and we'll send JSON of socket with the type of unsubscribed with a match ID of message.matchID. This basically means I'm done watching this match. I no longer want to receive live updates. Pretty cool. So now we're handling the message that we accept. It can either be a subscribe or an unsubscribe. So now we actually have to use it when we call wss.on connection, that is right here. And then right here above send JSON of a type welcome, we'll say socket.subscriptions is equal to a new set. So we're attaching a set directly to the socket object. And this allows the socket to remember what it's subscribed to. Then below this send JSON, we'll say socket.on message. We'll get the data of the message, and we'll simply call the handle message and pass in the socket and the data so you can properly handle the subscribes and unsubscribes. And we'll do a similar thing on socket.onError. So that's going to be on error right here. We don't get any data, and we will simply call the socket.terminate if something bad happened. We can do a similar thing with a socket.onClose. This is a very important one for memory, where if it closes, we can simply call our cleanup subscriptions to a specific socket. Finally, we have this function below that broadcasts that the match has been created to everybody, but now we need another function called broadcast commentary, which is going to accept the match ID that we want to get the commentary for, and then the comments themselves. And here we can use the broadcast to match utility function to broadcast to this specific match ID with a type of commentary and the data of the comment that we formed. Finally, we can now return this function, broadcast commentary, so that we can use it in the rest of our application. Of course, we'll be able to do that once we attach it to app.locals. That's going to be within our index.js. We have done a similar thing here for broadcast match created, but now we also want to get access to broadcast commentary, and that's going to be app locals broadcast commentary to broadcast commentary as well. And finally, we are ready to use it directly within our REST route. So if you head over here, when we're creating a specific commentary, that's going to be within the post request, immediately after we create it, we want to trigger a broadcast. So that's going to be if res.app.locals.broadcast commentary, just to make sure that we actually can call this function, res.app.locals.broadcast commentary, and notice that we want to pass the specific match ID. So that's going to be entry.matchID so that the server knows which room to send the message to. And then we're also going to send the entire entry. In this case, the entry is the actual commentary getting created. So what we have to do is rename this result to entry, or just use the word result right here, however your AI decided to call this variable. And that's it. We're all set. It's very similar to what we have done when we create a match. We immediately broadcast to the entire server that a new match got created. But in this case, when we create a new event within a specific match, then we let only the people interested in that match know that it happened. This is the most common use case for WebSockets. But now it's time to test the logic. And testing pub/sub requires observing different behaviors for different users. So we'll test it in different circumstances. First, let's test it through our terminals, the same way we did before. Make sure that your app is running, and then open up a second terminal, and we can split this one in half. In terminal A, this is going to be a general listener. You simply want to connect it to your server. And then terminal B will be the subscribed fan. So do the same thing, type wscat-c, ws, and then the actual URL to our WebSocket server, and run it. So now both have created accounts. Now, specifically for the subscribed fan, we actually want to subscribe them, right? That's what we have been working on. So type this, type subscribe to a match ID of 1, and press enter. So this one is now subscribed. Now, if you head over to HTTP and create a new match by heading over to post, matches, and you enter some kind of a body like football, JSM pool against the Drizzle United, for example, with a start and end time, like what we have done before, and you click send, you'll immediately be able to see a match created event on both terminals because this is being broadcasted to every single connected client. But now we want to create a new post commentary. So head over to post, matches, and use match number 1 because that is the one that we subscribe to right here. And then say commentary. And again, you'll have to type this out by hand, or actually this will be provided in the video kit link down in the description, so you don't have to type it out, or you can just press Command Z a couple of times to go back to what you had before. Either way, I'll provide it for you. So type an event. In which minute did it happen? Which number in the sequence is it? The period, the type of the event, who did it, and so on. Now, go ahead and click send. This is pretty cool, and it means that validation is working. Invalid commentary payload. Minutes expected a number, but in this case, we sent minute, so let's rename it, and click send. And you can see that a new match got created. But we didn't get an update on our second terminal. This now means that an angry fan is waiting to be updated, but they're not getting any updates. That's not good. And I don't want to hide any process for you. So what I did next is I told ChatGPT what I was trying to achieve, and I told it that I didn't see the commentary event update on the second terminal. AI is actually super good at spotting these little mistakes. So I told it, I haven't seen it. I even had a couple of typos because I was typing it so fast to get a solution, but AI doesn't care. It only cares about what you give it. So I provided some code, like all the different files that we created so far, and asked right here at the end, I said, let's get till the end, let me know if you see the issue or you need some more info. And then it said, yep, I see the issue immediately. Typically, it would take me like maybe 30 minutes up to an hour if it's a harder issue to find. And it found it quickly. So AI is pretty good for stuff like this. Here's how it explains it. Your pub/sub logic is never subscribing, so broadcast to match has nobody to send to. And the root cause is you're comparing the message type to the function subscribe in your WS handler. But message.type is a string, like subscribe. Subscribe without quote is the function reference, so this condition is always false. And the same issue happens with the unsubscribe. So the fix is in the handle message. We can simply copy paste this, or you can see that here it's using quotation signs. So back within the code where we have our server, where we're trying to figure out what happens on subscribe and unsubscribe, even though you can see that these are actual functions we created right here, we need to be focusing on strings of subscribe and unsubscribe. You can see how those little typos can cost us time. And then it said, After this, your terminal B will actually get type subscribed. The second bug is that we're inserting minutes into DB, but your column is probably minute. Nice catch. So basically, it's saying insert minutes, but your earlier code version used this, so one is wrong. So if your DB column is minute, which most likely it is, we have to switch it to minute here too. Let me just do a global search by pressing Command-Shift-P and search for minute. And you can see that indeed in the database, it says minute, minute, name minute, and so on. It is all minute. But here we're using minutes. So I'll simply replace this to minute, then get back to where we're actually attaching this event, which is going to be in routes commentary. And I will switch this over to minute and minute right here. After that is done, we can do a quick test after the fix. In the terminal A, we keep it running. In terminal B, we have to again try to subscribe. So let me do that. I will rerun both of these, but make sure that the app is actually running, which it is. So WSCat here, but let me actually clear the terminal so it's a bit easier to see. Run WSCat and run WSCat here. But now we want to subscribe to match ID, and we actually get back the event of subscribed, which is what we wanted to see. Perfect. And now we have already seen that if you create a new match, it'll be broadcast to everybody. But if we post a commentary to match 1, only the terminal B should receive the data and terminal A should not. So I'll open HTTP and again add a new commentary and click send. This time we have to switch it back to minute, but this is correct because that's what it says in the database. And click send. And take a look at this. We immediately got back the new broadcasted event through our tunnel directly to our second client with a type of commentary and all the data so we can immediately display it on the browser if this was a web app. But let's try to replicate that. If you go to your browser on localhost 8000 and duplicate it 3 times, we can even put it side by side. Then open up Developer Tools by pressing F12 on your keyboard to all 3 and open up the console. Now in the first browser tab, you want to copy and paste a code snippet that I'll provide to you within the video kit link down in the description, or you can pause the video and type it out by hand. Essentially, we're subscribing as a fan A, and this fan is only interested in what's happening within match 1. Then in the second tab, it's going to be very similar, but this time we're a fan B subscribing to match 2, and I used a different color right here. Again, I'll provide this message as well, just so you don't have to type it out by hand in case you want to test it for yourself. And then finally, in the third browser, you just want to connect to a WebSocket, but you're not interested in any matches. You can get all of these 3 in the video kit in case you want to follow along, but it's fine if you just take a look at what's happening on my screen. And then press enter on all 3 of these. And you can see that we get fan A, match 1 only, with a type of welcome, and it subscribed to match 1. Perfect. Then fan B, it got welcome, and it also got subscribed to match 2. And in tab 3, we got a lurker, somebody who's not subscribed to any matches. Now, as before, if I open up my HTTP and we want to trigger events for 2 different matches, one after another, and then watch the console, we can leave the same event right here. But first, we're going to add that goal to the match 1 commentary by clicking send, and pay close attention to that terminal 1, 3, 2, 1, and match 1 got updated immediately with the correct data. Now let's try to add the same one to commentary 2, and you can see that it got updated, and tab 3 didn't get updated, which just proved us that your WebSocket is not leaking data, while tab 1 and tab 2 prove that they are seeing data for things they care about, nothing else. And that's it. It's that easy to implement a pub/sub real-time WebSocket connection. Of course, with bigger applications and more user traffic, there's going to be more problems to solve. But in general, this is how you will do it all the time. With that in mind, let's go ahead and push our changes. First, we have to check out to a new branch. I'll call it feat pub/sub, and make sure to add the -b flag to actually create a new branch. Then run git add dot git commit -m implement pub sub broadcasting for commentaries, and then git push. Once that is done, head back over to your repo and open up a pull request. And let's let CodeRabbit do its job. In this PR, we introduced a new commentary feature with the REST API endpoints for fetching and creating match commentary. But then we created per match WebSocket subscription management for targeted broadcasts. This is how it works. The client sends a message of a type subscribe to our WebSocket server, which then calls our subscription registry, adds the socket to the match ID group, and then later on, when a commentary is posted, this user immediately receives the commentary data. In this case, we have one piece of feedback, which is a major issue. The default limit should align with max limit of 100. Currently, it defaults to 10, even though max limit is 100. This yields smaller result sets than intended. Use the max limit as the default. Okay, this is a super simple one-line fix that you can implement if you want to. With that in mind, let's go ahead and merge this PR. Congrats! You just implemented the most important part of this application. And you've effectively learned not only how WebSockets work for broadcasting the data to all the clients, but you learned about the pub-sub subscription pattern so that your clients can subscribe for specific events. Congrats! In this lesson, we'll stress test our WebSocket backend with 1,000 seated users. At first, everything works fine. APIs respond, connections open, and data flows. It all feels stable until real users kick in. Because with WebSockets, scaling doesn't just mean more traffic. It means hundreds of thousands of long-lived connections, messages arriving at unpredictable times, and users interacting in ways that you just can't simulate. And that's when things start breaking. Latency will increase, connections will drop, and the server can crash. Whatever can't go wrong eventually will. And a lot of developers think that monitoring here simply means checking whether the service is online or not. That's just uptime. But WebSocket systems need deeper visibility, like how long events and messages take to process, which handlers slow down under load, and when CPU or memory spikes during real usage. And that's exactly why APM matters. APM stands for Application Performance Monitoring. And in this project, I'll teach you how to use Site24/7's APM to monitor our WebSocket backend in production and catch bottlenecks early. It gives us insight into performance issues, runtime errors, resource usage, and even event loop delays without extra manual debugging. So let's implement it. Go to your application and open up the terminal. We can do it right here. We need to install the APM Insight agent by running npm apm insight --save and press enter. While that is going on, you can create a new file in the root of your application outside of the source. Let's call it apm insight node.json. It needs to be outside of the source, right next to the git ignore and drizzle config. And now you can head over to Site24/7 to grab the license key. The link is going to be down in the description, so just click it and then join for free. Once you're in, you can head over to admin, scroll down to developer, and then head over to device key. Then you can click show device key and copy the key for your account. Once you have it, go back to your application and create a new JSON object where you can type license key, and that'll be equal to the key you just copied. Then you'll also need to type in your app name, which is going to be set to sports, and finally a port where this agent will run. That's going to be something like 10,000. Now, the only thing you need to do to actually activate it is open up your backend application. That's within index.js. And then right at the top of it, before any import statements, add import agent API coming from APM Insight, and then say agent API .config. This will turn it on and it'll start monitoring your application. Now, if you restart your application by pressing Control C and then running it again, I guess I can do that in any of these terminals, you'll be able to see that it'll run successfully, but then you'll also see a new folder created for you, APM Insight Data. Currently, it has only one log that you can see right here. Later on, we'll have more, and we'll be able to track all of it from the Site 24/7 dashboard. With that, our APM is now set. Believe it or not, that's it. All it took was 2 lines. But to see it in action, we'll first have to deploy the application. So in the next lesson, let's go ahead and deploy this API. I mean, that's the moment you've been waiting for, right? And then later on, we'll seed it with 1,000 users and a lot of sports events. And then we'll go back to Site 24/7 to check how our app behaves under load. To start deploying your project, head over to your Hostinger dashboard, then to the websites list, and continue the setup. Here, you'll be able to choose whether you want to create a new one or bring your website to Hostinger. We'll go with the new one. And then right here at the bottom, you'll be able to select Deploy your Node.js web app. This is for advanced user, and you definitely are one after building this WebSockets application. So click Deploy your Node.js web app. And at this point, it might be a good idea to get your domain name as well. You can choose something like sports, and then you can enter your name or something, or you can think of something entirely unique to you. It can also be something related to WebSockets. Once again, totally up to you. For now, I'll use a temporary domain, and then you'll have to import your Git repo. So just click Continue with GitHub, and you can see that I granted access to this repo. Let me show you how you can do that. If you head over to your GitHub settings, and then scroll over to Applications at the bottom of the Integrations tab, then find Hostinger and click Configure. Here, you'll need to sign in, and once you're in, you can either select all repositories or select specifically the sports repo that we created for this project, and then click Save. After that, you can head back over to Hostinger, reload the page, and then go through the process again and search for the sports application. Then select it and click Continue. This might take some time as it's now processing the repo, taking a look at its code base, and figuring out which framework it is. So you can see, as I was speaking, it figured out that it was the Express framework on the main branch using Node.js version 22, and also it figured out the root directory. Now we can also change the settings right here, or just leave it as default, and then we can change the environment variables. Here we can import our own env. You simply need to find your application, and then we need to uncover hidden files. On macOS, that's Command-Shift//, and then you'll be able to see all of these files starting with a dot. So simply select this .env, or if you weren't able to find it, you can simply enter them manually. Make sure that you have your database URL, the port, the host, and the Arcjet key, as well as the Arcjet environment, which here we can set to production. And then click Finish. You'll see added 5 environment variables under a temporary domain. So go ahead and click Deploy. This is going to take some time to deploy from GitHub, and you'll be able to see all the server logs right here. Now, you can see the deployment failed, and that's totally okay because we have access to the logs. So if you click View Details, you'll see more details about the build failed right here, and that's totally okay. Actually, I wanted this to happen so that you can copy this custom domain and then add it over to your environment variables, because no longer will we be on localhost. Rather, we have to add a new API URL variable and set it to this URL right here, but make sure that it is under HTTPS and press Save. This will redeploy it. Oh, and I clicked redeploy, but it's going to fail again, and that's because I didn't point to the starting point of a server properly. So what you want to do is head over to Settings, and instead of index.js being the entry file, you want to make it source/index, because that's where that file is positioned. Now it'll start building it for real because it'll be able to find the main server file. And there we go. You can see that in a couple of seconds, it's going to say completed, which means that we have our active application. The only thing you have to do right now is head over to the overview of your deployment and then click on the URL. Check it out. If you zoom in a lot, it's going to say hello from Express Server. And if you open up the URL and head over to matches, you'll also be able to see a nice list of all of the matches that we have added so far. Currently, we have 4. They're all football matches between real teams and JSM United. So that's great to see. That means that our API is now deployed to the internet. But not only that, you can see that it has page speed insights of 99, and it also has HTTPS security. And if you haven't already, you can connect your own professional domain to it, which is always a plus. But now it's time to test it for real to see what this architecture can really do. We have built the system, but we need to know whether it'll hold up when many actions and events get through. So now we're gonna run a 1000 point speed seed. We're gonna send a massive amount of data to our WebSocket API to see exactly how our architecture handles the pressure in real time. And doing this is gonna be helpful because it'll generate a lot of traffic for us to analyze. Then the agent coming from Site 24/7 will allow us to do a much more detailed analysis, and we'll be able to monitor it all on Site 24/7. We'll do that as soon as we seed it. But for now, we want to see how the connections will hold up and if our subscription logic is actually filtering out the noise like it was in our previous example. First things first, make sure that your application is running. I have so many terminals right here, but I'll close them and just run them right here in this big one by running npm run dev. Then head over to your .envs. That's going to be right here. And let's make sure that we have all of the envs. First, we have to have a couple for the database, such as the database URL. Then we have to have the port. This is for the Express server. And host, sure, we can leave it here. So I'll say port and host. Then after that, we have the settings and keys for Arcjet. And finally, we need to add the API URL that we added also in the production website. So that's going to be API URL is set to http :// localhost 8000, as opposed to the production one, which is real hostinger deployed URL. And of course, for production, we'll use that one. So we can say API URL and then your real production URL, just so people know they have to change it in production. Perfect. I'll also add a couple of additional envs, such as broadcast set to 1, delay in milliseconds, which I'll set to 250, and a match count is going to be set to 0. I'll explain these soon. But for now, let's set up our WSCat so we can monitor everything happening right here within our terminals. Good thing that I ran the application here because we're going to use this double window to run 2 separate WSCat instances. So the terminal A is going to be the generic listener. So we simply want to connect and not type anything within it. That is WSCat-C ws : / localhost 8000 / ws. And we got a type of welcome. Then in the second one, this is going to be the subscribed fan. So I'm going to type the same thing, but then we want to subscribe to a match. So we'll do an object with a type of subscribe to a match ID of 1. Make sure to type it exactly like this. And you'll be able to see an event that we get back that says subscribed. Nothing we haven't seen so far. And just for fun, sorry for the flash of screen, what do you say that we also open up our terminals and split them in 3 as we did before? So I'll take this page, I'll duplicate it a couple of times, and then we'll put it side by side right here. There we go. And in all of them, we can press F12 to open up the console. Perfect. Now we'll use very similar messages to what we did before. You can find them in the video kit link down in the description. So here we'll enter 1. This is a browser fan that is subscribed to match 1. Then we'll have a second one, subscribe to match 1 only. Or you know what? We can subscribe this one to match 2 as well. So I'll say fan.send JSON stringify match 2. There we go. Subscribe to match 2 as well. And then finally in the third tab, this one will not be interested in any matches. Now we have to get some kind of data that we're going to seed our application with. So right under source, create a new folder and call it data. And within it, create a new data.json file. Within this JSON, you can either copy and paste the JSON from the video kit link down in the description, or if it's too long, I might just leave it as a JSON file, so you can just drag and drop it right here. But in general, it should look something like this. It's going to be absolutely huge. You can see right here that it has 17,000 lines. That's a lot of data that we want to fill this application with in a super short amount of time. Now notice that I didn't import it as JSON right here. So what I'll do instead, I'll delete the JSON file, download it manually, and then just drag and drop it here. That way it's going to be simpler and it's going to be correct. Now that we have the data file, we want to create another folder and call it seed. And within it, create a new seed.js file. You'll find it in the video kit link down in the description, so simply copy it and paste it here. This function will go through the data JSON and make calls to API routes that we created to create a commentary. Nothing special. You can also prompt any AI agent to create this function for you. But yeah, basically, we're going to rapidly seed all of this data into our application just to see how well it handles it. Then you have to head over to our package.json, and we have to add a script to be able to run this seed function. That's going to look something like this, seed, and it'll be set to node, source, seed, seed.js. That's it. Now in source, index.js, that is right here, comment out the Arcjet security middleware, so we don't bother it with all of this data, at least not right now. And then in a new terminal, which we can do here, I mean, since we have the browsers active, we don't have to have these two active. So right here in one of these, I'll run npm run seed and make sure these are open. And as soon as you run the seed function, you will have sent 1,000 live events through your system. And let's see if the architecture crashes. There are goals, there are smooth pulls, there are kickoffs, there's quick single takes, there's a lot of stuff happening right here, and you can see the match IDs. Now, these are our fans. Unfortunately, nothing is happening under matches 1 or 2, but let's say that fan B subscribes to a new match. So right here, I'll send a fan A subscribe event to match, let's do 15, because I've seen that move. And I'll also do a subscribe to match, let's do 13. And now you'll be able to see new data pieces coming in specifically for match 13 and match 15. And for example, the first one might want to subscribe to a match number 12. And then this one will get updated when something happens on match 12. The reason why I'm speaking so fast is because there's so much stuff happening right away. You can see browser fan A is getting updates on match ID 12 as they're happening. Here we're getting updates on match 15 and 13. And I feel like just I'm a newscaster on a huge sports event casting hundreds of thousands of matches. This is absolutely crazy. But what matters most is that you can see that our app is actually handling it. This proves that the hybrid REST and WebSocket architecture we built today is more than serious enough for serious live traffic. Now, could we make it even better? I mean, sure, we could add some caching, we can dive into some more advanced WebSocket comments. If you want to have a full course on JS Mastery Pro about WebSockets, let me know in the comments down below and I'll make it happen. But for now, just take a look at what you've built. You've engineered a high-performance sports engine from scratch. You're now officially ready to handle real-time data. And while it's seeding, I'll go back to site 24/7. You can find your app named Sports, and when you click on it, you'll see different backend metrics as soon as it starts receiving requests. Make sure to load some pages from the front end on the deployed site, such as heading over to /matches and so on. And keep in mind that it may take a couple of minutes for site 24/7 to detect them. So just keep refreshing. Now, APM, or Application Performance Monitoring, is a way to keep an eye on how well the app is working. In the site 24/7 APM dashboard, you can check out all the different important metrics. You can also see the AppDeck score, which shows how happy your users are, average response times, and request throughput and request count. All of these issues help us spot performance issues early and understand why an app feels slow or unreliable. And most importantly, fix problems before users notice. And with that, we're done. You've now gone end to end, from understanding how WebSockets work to building a real-time backend and deploying a live sports scoreboard API that stays online, scales correctly, and handles thousands of users and events. This isn't a project that only works on localhost. This is a production-ready, real-time backend. So you haven't just learned WebSockets. You understand when to use them, how to design them, how to deploy them, and how to make them reliable. And that's a huge milestone. But here's the next step. In this course, I intentionally focused on the backend engine. The front end for this sports app, the live UI, animations, interactions, the full polished experience, is built inside JS Mastery Pro. When you become a member, you won't just get access to this front-end build, which we'll do entirely using AI agents, so you'll learn a lot about AI-assisted development, but you'll also get access to the ultimate Next.js course, web animations with GSAP, complete testing course, and upcoming courses like Backend, React Native, and more. As part of the membership, I'll also show you how to build a beautiful, modern sports frontend connected to this WebSocket server you just created, and then enhance the entire workflow using free AI tools. And when you join, you'll get access to this project, plus all current and future courses included in the membership. Oh, and I'm also working on a couple of very big courses, from backend to ultimate AI engineering and more. So if you join, you'll be the first one that can use them when they're out. This is your jump from tutorials to building real systems. Let me know in the comments what you want to do next. More AI engineering, more real-time systems, or more advanced full-stack projects. Huge congrats on coming to the end of this amazing course. You'll learn so much about WebSockets, both in theory and in practice. Go check out jsmastery.com. Thank you for watching, and I'll see you in the next one. Have a wonderful day.